Imagine something so huge, so powerful, and so intense that it makes our sun look like a tiny, flickering spark. Now, picture this monstrous star burning with a fury so great that it could blast entire solar systems apart with its mere breath. This is not a flight of science fiction. It is real. Somewhere, far out in the vast, star-dusted darkness of the cosmos. Astronomers have found the biggest and most terrifying star ever discovered. Its size, its heat, its raw, untamed energy are beyond anything we can truly and viscerally comprehend. When we look up at the serene beauty of the night sky, we see a tranquil scattering of tiny, twinkling dots. They seem so small, so peaceful, just delicate pinpricks of light against the velvet black. But this is a profound illusion. A deception born of immense distance. Those little lights are, in fact, gigantic, blazing balls of fire. They are cosmic furnaces of unimaginable violence. Deep within their cores, powerful nuclear reactions are constantly and ferociously taking place, fusing the very atoms of the universe and releasing a torrent of energy that lights up entire galaxies, that creates the conditions for planets like our own to exist, and that is so immense that its gravity can bend the very fabric of space and time itself. But not all stars are created equal. Some, like our own sun, are relatively calm and steady. Cosmic home fires that have been shining peacefully for billions of years and will continue to do so for billions more. Others, however, are of a completely different order. They are the true giants of the universe, behemoths of such monstrous proportions that they defy our everyday sense of scale. These enormous stars shine with a brilliance so fierce that they could easily swallow entire planets and still hunger for more. They are not just bright, they are terrifyingly and beautifully powerful. So, what exactly is a giant, say, in the precise language of astronomy? The word giant is not just a casual descriptor of size. It refers to a specific and often dramatic stage in a star's life. After a star has exhausted the primary hydrogen fuel in its core, the fuel it has been patiently burning for millions or billions of years, it undergoes a profound transformation. It begins to fuse heavier elements, like helium, in a shell that surrounds its now inert core. This new, more intense form of fusion creates a powerful, outward pressure that pushes the star's outer layers far out into space. The star begins to swell, to bloat, growing hundreds or even thousands of times larger than it was in its youth. This is the red giant phase, and it is a glimpse into the future of our own sun. But for stars that are born with a much greater mass than our sun, this process is even more extreme. These stellar titans do not just become red giants, they become red supergiants. And in the rarest, most extreme cases, hypergiants, colossal, celestial beasts of such unimaginable size that they could engulf entire solar systems. But how do scientists, from their distant vantage point on a small, rocky planet, even begin to measure something so unbelievably huge? They use units of measurement that are themselves almost beyond our comprehension. Our own sun, for example, has a radius of about 696,000 kilometers. It is a number so large it is difficult to visualize. But now, consider Betelgeuse, the famous red supergiant that marks the shoulder of the constellation Orion. Its radius can be up to 900 times larger than that of our sun. If you were to place Betelgeuse at the center of our solar system, its roiling, fiery surface would stretch far beyond the orbit of Mars, swallowing Mercury, Venus, and Earth in the process. And yet, even Betelgeuse is not the biggest. There is another star, a red supergiant named Scuti, that dwarfs it. This colossal star, a true cosmic leviathan, may have a radius up to 1,700 times that of our sun. That would make it large enough to stretch beyond the orbit of Jupiter if it sat at the center of our solar system. Imagine a single, blazing star, engulfing half of our planetary family. That is the scale we are talking about. But a star's terrifying size is not its only frightening trait. There is also its brightness, its luminosity, the total amount of energy it radiates into space every second. Our sun produces just the right amount of energy to warm our planet and to nurture the delicate chemistry of life. It is a steady, reliable, and life-giving star. But the largest stars are of a different, more violent temperament. They produce hundreds of thousands, or even millions, of times more light and heat than our sun. They burn through their immense reserves of nuclear fuel at a furious, unsustainable pace, shining with an incredible, almost desperate brilliance, but only for a short time. And when they die, they do not fade away quietly. They go out in a blaze of glory in a spectacular and universe-shaking explosion. Many of these monster stars are found in strange and exotic places in the wild, untamed frontiers of the cosmos. They are often found in faraway satellite galaxies, like the large Magellanic Cloud, a small, irregular galaxy that orbits our own Milky Way. These smaller galaxies often have a different chemical makeup than our own, with lower amounts of the heavy elements like carbon, oxygen, and iron, that astronomers collectively refer to as metals. This low metallicity environment makes it easier for the primordial clouds of gas and dust to collapse and form truly massive stars. These metal-poor galaxies are like cosmic nurseries for the extreme, for the giants, for the stars that push the very limits of what is physically possible. But in space, as in life, being big comes with a heavy price. The bigger a star is, the faster it lives, and the shorter its life. Its immense gravity crushes its core, forcing it to burn its fuel at an incredible rate. A star like our sun can live for a stately 10 billion years. But the biggest, most massive stars are lucky to survive for a few million years, a mere blink of an eye in cosmic time. These are not the gentle, ancient gods of the cosmos, watching over the universe with a patient, steady gaze. They are the fierce, blazing titans, the beautiful and terrifying giants of the night, living fast, dying young, and leaving a spectacular, and often beautiful, corpse in the deep, silent darkness of space. In the far and often unexplored corners of the cosmos, beyond the familiar, graceful swirl of our own Milky Way, lie galaxies so strange and so wild that they seem to break the very rules of how stars are supposed to form. These are not the quiet, orderly, and well-behaved galactic cities that we are used to. They are chaotic, raw, and bursting with a primal, creative energy. And they are the perfect homes for the true monsters of the universe. Some of the brightest and biggest stars ever discovered, colossal behemoths like Stephenson 218 and UY Scuti, were born in these bizarre galactic neighborhoods, far from the calm and gentle lanes of our own suburban spiral arm. These massive stars do not just pop into existence out of nowhere. They are the product of extreme and often rare cosmic environments, places that act like celestial pressure cookers, forging stars of almost unimaginable size and power. Many of these stellar giants are found in small satellite galaxies or in the dense, crowded hearts of galactic groups, places with a strange and often primordial chemical makeup, places where furious, galaxy-wide waves of starbirth, known as starbursts, are constantly and violently churning up the vast interstellar clouds of gas and dust. To truly grasp how these terrifyingly powerful stars are born, we must first understand the unique and often violent conditions that give rise to them. One of the key ingredients in the recipe for a giant star is something called metallicity. In the precise, and sometimes counterintuitive, language of astronomy. Metallicity refers to the abundance of any element that is heavier than hydrogen and helium. These heavier elements, which astronomers collectively call metals, include familiar substances like carbon, oxygen, and iron, all of which were forged in the fiery hearts of previous generations of stars and then scattered into space when those stars died. And here is the surprising and deeply important part of the story: the less of these metals a primordial gas cloud has, the easier it is for that cloud to collapse and form a single, truly massive star. This is because these heavy elements act as a very efficient cooling agent. They are able to absorb the heat from a collapsing gas cloud and then radiate it away into space. This cooling allows the cloud to fragment into many smaller and denser clumps, each of which will then go on to form a relatively small star, like our Sun, but in places with a lower metallicity, like the small satellite galaxies that orbit our own. The gas clouds are less efficient at cooling. They stay warmer, and they are less likely to fragment. Instead of shattering into 1,000 smaller pieces, the entire vast cloud can collapse under its own immense gravity into just one or a few very massive protostars. These metal-poor galaxies become cosmic star factories of a very different kind. They are not mass-producing the small, gentle, and long-lived stars that are common in our own galaxy. They are specializing in the creation of the rare, the extreme, the giants, the blazing titans of the cosmos. In these dense and chaotic stellar nurseries, a process of cosmic Darwinian competition takes hold. The first protostars to form, especially those in the densest, most gas-rich parts of the cloud, get a head start. Their growing gravity allows them to pull in more and more material from their surroundings, effectively starving their smaller, less fortunate neighbors. They grow fast and they grow large, devouring the primordial gas in a kind of cosmic cannibalism, a process where only the gravitationally strongest survive and thrive. But it is not just the initial conditions of the gas cloud that matter. It is also its dynamics. If the cloud is turbulent, if it is full of wild, chaotic motion, or if it is spinning at just the right speed, it can create a gravitational funnel, a process that can efficiently channel a vast amount of material towards the center, feeding the growing protostar with stunning speed. When this happens, when gravity wins a decisive victory over the outward push of gas pressure, a single star can grow to be dozens or even hundreds of times more massive than our Sun, even before its nuclear furnace has fully ignited. And there is a strange and beautiful cosmic irony in all of this. While it is harder to form these enormous stars, once they do exist, they completely dominate their environment. Their intense, powerful light and their ferocious stellar winds can reshape the entire star-forming region around them. Sometimes, the shock waves from their powerful winds can compress the surrounding gas clouds, triggering the birth of a new generation of smaller stars. Other times, their energy is so immense, their radiation so fierce, that they can completely halt any further star formation in their vicinity, effectively sterilizing their own cosmic cradle. It is as if a cosmic queen has been born, a queen who demands all the attention, and who refuses to let anyone else share her brilliant and dazzling spotlight. And here is one of the most fascinating things that scientists have discovered: it was likely much easier for these colossal, monster stars to form in the very early days of the universe. Back then, in the first few 100 million years after the Big Bang, the universe was a much simpler and much purer place. The first galaxies were filled almost exclusively with the pristine, primordial hydrogen and helium that had been forged in the Big Bang itself. There were no metals at all. This was the perfect and perhaps the only time for the formation of what astronomers call population 3 stars. The true first generation of stars to have ever existed. These ancient, primordial giants, born in a metal-free universe, could have grown to be hundreds, or even thousands, of times more massive than our Sun. We have never seen one of these population 3 stars directly. Their immense mass meant that they lived incredibly fast and died incredibly young. They're spectacular and universe-shaping, lives ending long, long ago. But the massive, behemoth stars that we do see today, shining in the distant, metal-poor corners of the cosmos, may be their direct descendants, their modern-day echoes. A faint and beautiful reminder of a time when the universe was younger, wilder, and far more prone to creating monsters. One of the best and most convenient cosmic laboratories for studying this kind of extreme starbirth is a small, irregular, and beautiful satellite galaxy that is our own. Celestial next-door neighbor, the Large Magellanic Cloud, or LMC. If the Milky Way is the vast, sprawling, and relatively orderly capital city of our local galactic neighborhood, then the LMC is the wild, untamed frontier, a rough, energetic, and often surprising place, full of cosmic wonders and dangers. The LMC is a dwarf galaxy, with only about 1/10 the mass of the Milky Way, and it is in a close and often violent gravitational embrace with our own, much larger galaxy. It is located about 163,000 light-years from Earth, and it orbits our galactic center like a loyal, if somewhat chaotic, companion. But despite its small size, the LMC packs a powerful, star-forming punch. In fact, for its size, it is incredibly and unusually prolific. It creates more high-mass stars per unit of gas than our own Milky Way does. The LMC is like a celestial forge, a place that is constantly and furiously hammering out new, brilliant, and often massive stars. Its sky is aglow with fiery, star-forming nurseries and vast, brightly lit clouds of ionized gas, known as nebulae. One of the most famous and most spectacular of these is a region called 30 Doradus, more commonly known as the Tarantula Nebula. It is a vast, sprawling complex of gas and dust, a cosmic spider's web of stellar creation, and it is one of the most active and most luminous star-forming regions in our entire local group of galaxies. So, what makes the LMC so special? It all comes down to a combination of chemistry and chaos. The gas in the LMC has a lower metallicity than the gas in the Milky Way. This means it is less efficient at cooling, and therefore less likely to fragment into a large number of small stars. The LMC does not go for balance and moderation. It goes for the extreme. It makes fewer stars, but the ones it does make are, on average, much larger and more massive. This makes it the perfect birthplace for the true giants of the cosmos, for the stellar behemoths that push the very limits of what is possible. One such behemoth, a star named WOH-G64, is hidden deep within the dusty confines of the LMC. It is a red supergiant of almost unimaginable proportions. It is over 1,500 times wider than our Sun, and it shines with a light that is 280,000 times brighter. And it is not just big, it is also in the process of slowly and beautifully falling apart. The behemoth star is shedding its outer layers in a steady, glowing breath, a powerful stellar wind that is enriching the surrounding interstellar medium with the heavy elements that have been forged in its deep, fiery heart. Because it is so relatively close, and because there is less obscuring dust in the line of sight between us and the LMC, it has become an invaluable cosmic laboratory. Telescopes like the Hubble Space Telescope and the Very Large Telescope in Chile can peer directly into its star clusters and its nebulae, and they can watch, in almost real time, as the cosmic drama of stellar life unfolds as the giants are born, as they live out their short and furious lives, and as they finally and spectacularly collapse into the silence of a black hole or a neutron star. And what makes this story even more fascinating is the idea that the Milky Way itself may be the ultimate cause of all this chaos. The immense gravitational pull of our own galaxy is constantly tugging and stretching the LMC, creating powerful tidal forces that stir up and compress its gas clouds, sparking ever more furious waves of star formation. And some scientists believe that billions of years from now, this long and often violent cosmic dance will reach its final spectacular climax. The two galaxies will collide and merge in a galaxy-wide display of celestial fireworks, with stars and gas clouds being flung out into space like glowing, beautiful sparks. The Large Magellanic Cloud is more than just a small satellite galaxy. It is a window into the past, a glimpse of what our own and other galaxies may have looked like in their younger, wilder, and more creative days. Its strange, lopsided structure, its metal-poor gas, its furious, star-forming nurseries. All of these are a reflection of a time when the universe was a more chaotic, more energetic, and more fertile place. And so, when we study the monster stars that are born within it, we are not just learning about the life and death of a single cosmic giant. We are peeking into the ancient and often violent drama that has shaped the very fabric of the cosmos itself. The Large Magellanic Cloud is not just our galactic next-door neighbor. It is a primordial furnace, a wild, beautiful, and powerful reminder that in the grand cosmic story, size isn't everything, but the extremes, the outliers, the monsters, they can often make all the difference. A hypergiant star is a member of the most exclusive and most extreme club in the entire stellar zoo. These are the true heavyweight champions of the cosmos, stars of such immense size, such incredible brightness, and such profound instability that they seem to defy the very laws of physics. They shine with a brilliance that can be millions of times greater than our own sun. And they are constantly shedding their outer layers in powerful, ferocious stellar winds. Streams of hot gas that are blown away by the sheer, overwhelming force of their own internal radiation, in the formal and often complex language that astronomers use to classify stars, the Morgan-Keenan, or MK system. A hypergiant is assigned to the very highest luminosity class, a special and rarely used category known as Class 0, but you will not often see this label in the scientific literature. It is a term that is reserved for the true, unambiguous monsters, for the stars that are not just big, but are also exhibiting clear and often dramatic signs of extreme instability. More commonly, hypergiants are described with the labels IA0 or IA+, while even the most massive and luminous red supergiants are not usually given this special designation. So, why are astronomers so captivated by these rare and often cantankerous stellar beasts? Because they are the key to understanding some of the most fundamental processes in the universe. How the most massive stars are born, how they live their short and violent lives, and how they ultimately and spectacularly die, often in the titanic and universe-shaping explosions that we call supernovae. Famous examples of hypergiants include the Pistol Star, a brilliant, blue hypergiant that is hidden in the dense, dusty heart of our own galaxy's center. It is one of the most luminous stars ever discovered, shining with the light of several million suns. There is Rho Cassiopeiae, a yellow hypergiant that is so bright it is one of the few hypergiants that is visible to the naked eye from Earth. And there is Mu Cephei, also known as Herschel's Garnet Star, a colossal red hypergiant that is one of the largest and most luminous stars known in our galaxy. The term hypergiant was first coined, in its earlier form of supergiant, in 1956 by the astronomers Feast and Thackeray, to describe a small class of stars that were anomalously and inexplicably bright. Later, in 1971, the astronomer Keenan proposed a more precise, spectroscopic definition. He suggested that the term hypergiant should be reserved for those supergiants that show a very broad and bright emission line in a specific part of their light spectrum, the H-alpha line, which is a specific red wavelength of light emitted by hydrogen. This broad emission line is a telltale sign of a very extended and often unstable atmosphere, and of a star that is losing a tremendous amount of mass through a powerful stellar wind. Today, Keenan's rule is still the one that most scientists use, and it leads to a sometimes confusing situation where a particularly large and stable red supergiant might actually be more luminous, in terms of its total energy output, than a smaller but more unstable and wind-driven star that is officially classified as a hypergiant. One of the key diagnostics that astronomers use to identify a hypergiant is the detailed shape of its spectral lines. In a hypergiant, these lines are often distorted in a characteristic way, a shape known as a P Cygni profile. This profile has a strong emission peak and a blue-shifted absorption trough, and it is the classic signature of a star that is surrounded by a dense, rapidly expanding shell of gas, a direct and unambiguous sign of extreme mass loss. But when it comes to the coolest hypergiants, the red and the yellow ones, this spectroscopic method is not as reliable. And so, for these stars, astronomers must rely on a combination of their immense luminosity and their directly measured, and often staggering, rates of mass loss. Stars that are born with more than about 25 times the mass of our Sun have a very different, and much more dramatic, life story than their smaller, more sedate cousins. They do not spend a long and peaceful life on the main sequence, the stable, hydrogen-burning phase of a star's life. Instead, they quickly evolve into brilliant, blue supergiants, shining with an intense and often unstable light. Then, as they age, they can go through a series of complex and often chaotic transformations. They can expand and cool to become red supergiants, and then contract and heat up again, sometimes oscillating back and forth between hot and cool phases in what astronomers call blue loops. Eventually, they will either explode as a spectacular supernova, or, if they are massive enough, they will shed their entire hydrogen-rich outer envelope and become a very special and very hot kind of star, known as a Wolf-Rayet star, the exposed burning core of a once mighty giant. But for the very most massive stars, those with more than about 40 times the mass of the Sun, the journey is even more direct and even more violent. These stars are so luminous, so powerful, that they can never become a stable red supergiant. The outward pressure of their own internal radiation is so intense that their outer layers are simply blown away before the star ever has a chance to cool down and expand. These are the stars that are destined to become hypergiants. Hypergiants live at the very top of the Hertzsprung-Russell diagram, the grand organizing chart of the stellar kingdom. They are the true cosmic royalty, occupying a region of extreme luminosity and a wide range of temperatures. They can be either young, freshly evolved, and still hydrogen-rich massive stars that have just left the main sequence, or they can be older, more evolved, and hydrogen-poor stars that have already passed through a red supergiant phase and have lost a significant fraction of their initial mass. Just looking at a star's position on the HR diagram is not always enough to tell the difference, but the older, more evolved stars are generally more unstable. Their atmospheres are puffed up, their surface gravity is weaker, and they are constantly teetering on the brink of a delicate and often violated balance point known as the Eddington limit. This is the critical point where the outward push of radiation pressure from inside the star becomes equal to the inward pull of its own gravity. A star that is shining at the Eddington limit is, in a very real sense, on the verge of blowing itself apart. And this is the realm where the hypergiants live. The yellow hypergiants, in particular, are thought to be post-red supergiant stars, stars that have already shed a significant portion of their hydrogen envelopes. The blue hypergiants, on the other hand, can be either pre- or post-red supergiant, their immense luminosity making them inherently unstable regardless of their evolutionary state. And most hypergiants do not shine with a steady light. Their brightness is constantly, and often chaotically, changing. They flicker, they pulse, they have sudden, violent eruptions. In the case of a special class of hypergiants, the luminous blue variables, or LBVs, these eruptions can be so powerful that the star can temporarily increase its brightness by a factor of hundreds or even thousands, becoming one of the most luminous objects in its entire galaxy, before it settles back down into a quieter, though still deeply unstable, state. Hypergiants are rare. They are ephemeral, and they are profoundly and beautifully violent. They are the fleeting and spectacular death throes of the most massive stars in the universe, a final, brilliant blaze of glory before they finally and inevitably collapse into the silence of a supernova and the darkness of a black hole. Hypergiants are not just huge, they shine with an almost unbelievable and often self-destructive brightness. As a star's mass increases, its luminosity does not just increase linearly, it increases dramatically, roughly as the mass to the power of 3.5. This means that a star that is 10 times more massive than our Sun is not just 10 times brighter, it is about 3,000 times brighter. And the hypergiants, with masses of up to 150 times that of the Sun, are millions of times more luminous. This incredible and often overwhelming brightness is the source of their profound instability. They are constantly living on the edge of the Eddington limit, the critical balance point where the outward force of their own internal radiation pressure is on the verge of overcoming the inward pull of their own gravity. Imagine a star as a delicate, gravitational dance between two opposing forces. Gravity is constantly trying to crush the star, to pull all of its matter down into the center. The outward pressure of the hot gas and the radiation generated by the nuclear fusion in its core is constantly pushing back, holding the star up. In a normal star, like our Sun, these two forces are in a state of beautiful and stable equilibrium, a state that can last for billions of years. But in a hypergiant, this balance is precarious, and often it is lost. If the luminosity of a star exceeds the Eddington limit, the outward push of its radiation will literally blow its outer layers off into space. This is not a gentle, steady, stellar wind. It is a series of violent, convulsive, and often eruptive mass loss events. This is the universe's ultimate safety valve, a built-in mechanism that prevents a star from becoming infinitely massive and infinitely luminous. One of the most famous and most dramatic examples of a star that is currently and violently exceeding its Eddington limit is Eta Carinae, a truly monstrous and deeply enigmatic star system that is located about 7,500 light-years away from us, in the heart of the beautiful and spectacular Carina Nebula. Eta Carinae is thought to be a binary system, with a primary star that may have been born with a mass of up to 150 times that of our Sun. It shines with a light that is about 4 million times brighter than our sun, a luminosity that places it firmly and dangerously in the realm of the hypergiants. And we have seen it in the act of blowing itself apart in the mid-19th century, between the years 1837 and 1856. Eta Carinae underwent a massive eruptive event known as the Great Eruption. Over a period of about 2 decades, the star shed an enormous amount of mass, at least 10 to 20 times the mass of our sun, in a series of violent outbursts. During this time, it became the second brightest star in the entire night sky. Its light so bright that it was used by sailors in the southern hemisphere for navigation. The material that was ejected in this eruption has now formed a beautiful and iconic bipolar nebula around the star, the Homunculus Nebula, a ghostly hourglass-shaped shroud of gas and dust that is still expanding outwards at a speed of over 600 kilometers per second. The cause of the Great Eruption is still not fully understood, but it was almost certainly a super-Eddington event, a moment when the star's internal luminosity so dramatically exceeded its Eddington limit that its outer layers were violently and catastrophically unbound. The mechanism by which hypergiants lose mass is a complex and still not fully understood area of astrophysics. Massive stars lose mass through line-driven winds. The atoms in their outer atmospheres, particularly the metals, are very good at absorbing photons of specific wavelengths, or spectral lines. This absorption gives the atoms a little outward push, and the cumulative effect of billions of such pushes is what drives a steady and relatively gentle stellar wind. But in the extreme, and often metal-poor environments of hypergiants, this mechanism may not be sufficient to explain the staggering rates of mass loss that are observed. This has led to the proposal of other, more exotic, mechanisms. One of these is continuum-driven winds. In this scenario, the radiation field is so intense that it is not just the absorption in spectral lines that matters. The sheer, overwhelming pressure of the entire continuum of radiation is enough to push on the free electrons in the star's atmosphere, which then drag the protons along with them, creating a much more powerful and much more efficient form of mass loss. This is a particularly important idea because it could help to explain how the very first metal-free population 3 stars were able to regulate their own growth and to shed their outer layers, even in the absence of the heavy elements that are needed for line-driven winds. Another, even more speculative, idea is that hypergiants might experience deep internal explosions. In the vast convective interiors of these stars, the process of heat transfer can sometimes become inefficient, leading to the buildup of vast, superheated bubbles of plasma. These bubbles could then rise and burst through the star's surface in a series of powerful and often geyser-like eruptions. This could be a mechanism for the kind of episodic and often clumpy mass loss that is observed in stars like Eta Carinae. And there is another, curious and deeply counterintuitive concept that may be at play: the pseudo-photosphere. The photosphere is the visible surface of a star, the point at which it becomes opaque to its own radiation. But in a hypergiant with a very dense and powerful stellar wind, this visible surface may not be the true physical surface of the star at all. It may be a false surface, a pseudo-photosphere, that is formed in the optically thick wind itself, far above the star's true and much hotter surface. This could help to explain the puzzle of the yellow hypergiants, stars that are as luminous as blue hypergiants, but have a much cooler, yellow, surface temperature. Perhaps they are not truly cool stars at all. Perhaps they are hot, luminous blue variables that are currently enshrouded in a thick, cool, and opaque pseudo-photosphere, a temporary and beautiful cosmic disguise. The classification of stars is a complex. and often subtle, art. The Hertzsprung-Russell diagram, with its beautiful and orderly arrangement of stars into categories like dwarfs, giants, and supergiants, provides a powerful organizing framework, but nature is often messier and more creative than our neat, human-made categories would suggest. And nowhere is this more true than in the exotic, and often blurry, world of the hypergiants. These stars, with their extreme luminosities and their profound instabilities, often defy easy classification. They exist in a dynamic and often transitional state, and their properties can change dramatically over very short. Human timescales, the luminous blue variables, or LBVs, are a prime example of this classificatory challenge. These are massive and deeply unstable, stars that can undergo sudden, and often unpredictable, changes in their brightness, their temperature, and their spectra. In their quiescent state, they are hot, blue, and incredibly luminous, placing them in the same region of the HR diagram as the blue hypergiants. But during their eruptive phases, they can dramatically increase their brightness, and their atmospheres can become so opaque that they develop a cool pseudo-photosphere, temporarily appearing as a yellow or even a red. Supergiant. The star P Cygni is the prototype for this class, and it is a star that has been observed to change its spectral type, its temperature, and its brightness multiple times over the last few centuries. So, is an LBV a hypergiant? Or is a hypergiant an LBV? The answer is not always clear. Some astronomers consider all LBVs to be a type of hypergiant. Others argue that the term hypergiant should be reserved for those stars that show persistent signs of extreme mass loss, while the term LBV should be used for those that exhibit the characteristic eruptive variability. It is a debate that is as much about semantics as it is about physics, but it highlights the fact that these stars are living in a very unstable and very transitional phase of their lives. A similar blurriness exists at the boundary with the Wolf-Rayet stars. These are the hot, exposed, and hydrogen-poor cores of very massive stars that have already shed their entire outer envelope. One particular subclass of these, the WNL stars, are Wolf-Rayet stars that are still relatively rich in nitrogen and may still have some hydrogen remaining. These are thought to be the immediate evolutionary successors to the LBVs and the blue hypergiants. They are the stars that are on the very last step of their journey before they explode as a supernova. But even here, the lines are not always clear. Some LBVs, in their quiescent state, have been observed to have spectra that are almost indistinguishable from those of WNL stars. And some stars that were once classified as WNL stars have been seen to suddenly change their behavior and to look more like blue hypergiants. The rapid rotation of a massive star can further complicate the picture. A very rapidly rotating star can shed its outer layers so efficiently through a process of rotationally induced mixing and centrifugal mass loss that it can skip the red supergiant and the LBV phases entirely, evolving directly from a main sequence star into a Wolf-Rayet star. All of this is to say that the lives of the most massive stars are not a simple, linear, and predictable journey. They are a complex, chaotic, and beautiful dance, a story of transformations, of disguises, of sudden and violent changes. The neat categories that we have created are just a human attempt to impose order on this beautiful cosmic chaos. But the universe is not always so easily pigeonholed. And the hypergiants, in all their strange, beautiful, and unpredictable glory, are a powerful and humbling reminder that nature's creativity will always and wonderfully exceed the limits of our own human imagination. Red supergiants are the true, volumetric giants of the stellar kingdom. They are not the most massive, nor the most luminous of stars, but in terms of their sheer physical size, they are without peer. These are stars that have swelled to such colossal proportions that they could easily engulf the orbits of the inner planets of our own solar system. They are the great, bloated, and beautiful behemoths of the cosmos, stars in the final, and often dramatic, stages of their long lives. In the formal, Morgan-Keenan system of stellar classification, red supergiants are assigned to luminosity class 1, the class of the supergiants, and their red designation comes from their relatively cool surface temperatures, which place them in the K or M spectral classes, two of the most famous and most visually stunning. Examples of red supergiants are Betelgeuse, in the constellation Orion, and Antares, the brilliant, fiery heart of the constellation Scorpius. These are two of the brightest stars in our night sky, and their distinct reddish hue makes them easily recognizable, even to the casual naked eye observer. The classification of a star as a supergiant is a subtle art. It is not just a matter of its size or its total energy output. It is a spectroscopic determination, a judgment that is based on the detailed features of a star's light. The spectrum of a star is like its fingerprint, a unique pattern of dark absorption lines and bright emission lines that reveals a wealth of information about its temperature, its chemical composition, and, crucially, its surface gravity. The surface gravity of a star is a measure of how strong the gravitational pull is at its visible surface. A small, dense star, like a white dwarf, will have an incredibly high surface gravity. A large, puffy, and diffuse star, like a red supergiant, will have a very low surface gravity. And this difference in surface gravity has a direct and observable effect on the star's spectrum. In a low-gravity environment, the atoms in the star's atmosphere are less compressed, and the spectral lines they produce are narrower and sharper. By carefully measuring the width of these gravity-sensitive lines, astronomers can distinguish between a normal, main-sequence, dwarf star, a more evolved giant star, and a truly colossal supergiant star, even if they all have the same surface temperature. And even within the supergiant class, there are finer distinctions. A star can be a normal supergiant, a bright supergiant, or, in the most extreme cases, a hypergiant. The term hypergiant is, as we have seen, almost never applied to the red supergiants, with a few notable and highly unstable exceptions like VY Canis Majoris and NML Cygni. Red supergiants have surface temperatures that are relatively cool by stellar standards, typically below 4,100 Kelvin, which is cooler than our own sun. But what they lack in temperature, they make up for in size. They can have radii that are several hundred, or even more than 1,000, times that of our sun. And because their luminosity is proportional to their surface area and the fourth power of their temperature, their immense size means that they are incredibly bright. A typical red supergiant can be tens of thousands, or even hundreds of thousands, of times more luminous than our sun. There is, however, a theoretical upper limit to how large a red supergiant can be. This is known as the Hayashi limit. A star that expands and cools beyond this limit becomes fully convective and dynamically unstable. It can no longer maintain a state of hydrostatic equilibrium. The largest and most luminous red supergiants are thought to live right at this theoretical edge, their vast, tenuous atmospheres constantly teetering on the brink of gravitational instability. And these stars are not born this way. They are the evolved descendants of massive, hot, and blue main-sequence stars, stars that were born with a mass of between about 10 and 40 times that of our sun. As these massive stars exhaust the hydrogen fuel in their cores, they begin to burn hydrogen in a shell, which causes their outer layers to expand and cool, transforming them into the red supergiants we see today. Stars that are born with a mass of more than about 40 solar masses are so luminous that they are never able to become red supergiants at all. They shed their outer layers and evolve through a different and hotter evolutionary path. And the red supergiant phase itself is a relatively short one. A massive star will only spend a few million years in this bloated state before it exhausts its remaining nuclear fuel and ends its life in a spectacular core collapse supernova. But during this short and often turbulent phase, red supergiants play a crucial and beautiful role in the chemical evolution of the galaxy. They are prodigious losers of mass, their powerful, slow, and dense stellar winds carrying away a vast amount of material, enriched with the heavy elements that have been forged in their deep nuclear furnaces. This material, which includes carbon, nitrogen, and oxygen, is then scattered into the interstellar medium, where it will become the raw material for the next generation of stars, planets, and perhaps life. The beautiful, glowing clouds of gas and dust that we see surrounding many red supergiants. The nebulae that are the precursors to planetary nebulae are a direct and stunning visual testament to this process of cosmic recycling, a process that is essential to the ongoing creative life of the galaxy. The material that surrounds a red supergiant, the circumstellar gas and dust that has been shed from the star in its powerful stellar winds, is a rich and complex environment, a natural cosmic laboratory for studying the physics and chemistry of the interstellar medium. And one of the most fascinating phenomena that occurs in this environment is the presence of masers. A maser is the microwave equivalent of a laser. It is a source of intense, coherent, and highly directional microwave radiation. And the extended, and often dense, atmospheres of red supergiants provide the perfect conditions for these natural cosmic masers to form. They are typically produced by molecules like water vapor, silicon monoxide, and the hydroxyl radical, and they are a powerful tool for studying the properties of the circumstellar environment. By using a technique known as very long baseline interferometry, where the signals from multiple, widely separated radio telescopes are combined. Astronomers can create images of these master sources with an incredible and almost unbelievable angular resolution. This allows them to map the detailed, three-dimensional structure and motion of the gas clouds around a red supergiant, to measure the speed of the stellar wind, and even to get a direct and highly precise measurement of the star's distance through the method of parallax. This technique is revolutionizing our understanding of the mass loss process in these evolved stars, and it is helping us to build a more accurate three-dimensional map of our own Milky Way galaxy. The chemical composition of a red supergiant's atmosphere also tells a beautiful story of its deep and often hidden internal evolution. While the outer layers of the star are still mostly composed of the primordial hydrogen and helium from which it was born, the star's vast convective envelope can dredge up material from the deeper nuclear burning regions. This process brings the products of fusion, like carbon, nitrogen, and oxygen, to the surface, altering the star's atmospheric composition in a predictable and observable way. By carefully measuring the abundances of these elements in a red supergiant spectrum, astronomers can get a direct glimpse into the nuclear processes that are happening deep within its fiery heart. And the evolution of a red supergiant is not always a slow and steady process. The most massive of them can sometimes go through blue loops, temporary, and often rapid excursions on the HR diagram, where they contract and heat up to become blue supergiants before they expand and cool down again. These loops are thought to be caused by a complex interplay between the star's mass, its rotation rate, and its chemical composition, and they are a sign of the deep and often chaotic instabilities that can occur in the final stages of a massive star's life. A crucial and sometimes confusing point of classification is the distinction between a true red supergiant and a very luminous star on the asymptotic giant branch. AGB stars are the evolved descendants of lower mass stars, like our Sun. They are also large, cool, and luminous red giants, and the most massive of them can be as bright and as large as the least massive red supergiants. But they have a fundamentally different internal structure and a very different ultimate fate. A true red supergiant is a massive star that will go on to fuse heavier and heavier elements in its core, eventually forming an iron core and exploding as a core collapse supernova. An AGB star, on the other hand, has an inert carbon-oxygen core, and it will end its life by shedding its outer layers to form a planetary nebula, leaving behind a white dwarf. The distinction between these two classes of stars is a subtle but important one, and it highlights the fact that nature does not always fit into our neat and often oversimplified classificatory boxes. But for the true red supergiants, the end is always the same, and it is always spectacular. After a life that is measured in the millions, not the billions, of years, after a long and often turbulent journey across the HR diagram, after having enriched the galaxy with the heavy elements that will one day form new stars and new worlds, the iron core of a red supergiant finally and catastrophically collapses. In a fraction of a second, the star is gone, its immense mass and energy released in a single, brilliant, and universe-shaking flash of light. A supernova explosion that will briefly and beautifully outshine its entire host galaxy. It is a final and spectacular act in the life of a true cosmic giant, a final gift to the ongoing, creative, and beautiful story of the cosmos. A subgiant is a star that is in a fascinating and often fleeting transitional phase of its life. It is a star that has exhausted the hydrogen fuel in its core and has begun its journey away from the stable, long-lived main sequence and towards its ultimate fate as a giant star. It is, in a sense, a star in its adolescence, a star that is no longer a child, but not yet a full-grown adult. The term subgiant has two related meanings in astronomy. It refers to a specific luminosity class in the Morgan-Keenan system of stellar classification, a class of stars that are more luminous than main sequence dwarfs, but less luminous than true giants. And it also refers to a specific evolutionary stage in the life of a low to intermediate mass star. The subgiant phase begins at the moment that a star's core ceases to fuse hydrogen. Without the outward pressure of fusion to support it, the now inert helium core begins to contract and heat up under its own gravity. This, in turn, heats up the shell of hydrogen that surrounds the core, causing it to ignite and to begin fusing hydrogen into helium in a thin and often intense shell. The energy from this new shell-burning source causes the star's outer layers to expand and cool. On the Hertzsprung-Russell diagram, the star's evolutionary track moves horizontally to the right, towards the cooler, redder side of the diagram, while its luminosity stays roughly constant, or even increases slightly. This horizontal track is known as the subgiant branch. The duration of this subgiant phase depends on the star's mass. For a star like our Sun, it will last for a few 100 million years. For more massive stars, it can be much shorter, only a few million years. This is why subgiants are relatively rare in the sky. We are simply not likely to catch a star in this brief transitional phase. As the hydrogen-burning shell continues to add more helium ash to the core continues to grow in mass and to contract. Eventually, for a star like our Sun, the core will become so dense that it is no longer supported by normal gas pressure, but by the strange quantum mechanical force of electron degeneracy pressure. At this point, the star's evolution accelerates dramatically. The degenerate core heats up, the hydrogen-burning shell becomes even more intense, and the star's outer convective envelope expands rapidly, causing the star to move almost vertically up the HR diagram, on a path known as the red giant branch. The subgiant phase is a crucial and often complex turning point in a star's life, and its detailed behavior depends sensitively on the star's initial mass and chemical composition. For stars with a mass less than about 2 solar masses, the transition from the main sequence to the red giant branch is a relatively smooth one. But for more massive stars, the transition is more dramatic. The helium core can grow so massive that it exceeds a critical limit, the Schoenberg-Chandrasekhar limit, even before it becomes degenerate. This triggers a rapid collapse of the core and a rapid expansion and cooling of the outer layers, causing the star to move very quickly across the HR diagram. This rapid evolution is what creates the Hertzsprung gap, a sparsely populated region of the HR diagram that is often seen in the color magnitude diagrams of intermediate-age star clusters. Some subgiants, as they make their journey across the HR diagram, can pass through a region known as the instability strip. In this region, the star's atmosphere becomes unstable to pulsations, causing the star to rhythmically expand and contract, and to vary in brightness. These pulsating subgiants are known as delta Scuti variables, and in a few rare cases, even more massive stars can become classical Cepheid variables during their brief subgiant phase. The study of subgiants is a crucial tool for astronomers. Because the subgiant phase is so short, the point at which stars in a cluster turn off the main sequence and move on to the subgiant branch is a very precise indicator of the cluster's age. By carefully modeling the subgiant branches of globular clusters, astronomers can determine their ages with incredible precision, which in turn allows us to place a lower limit on the age of the universe itself. And in recent years, with the advent of high-precision exoplanet detection techniques, we have even begun to find planets orbiting subgiant stars. These discoveries are providing us with a fascinating and often surprising new window into the late stages of planetary system evolution, showing us what might happen to a planetary system when its central star begins to die. The subgiant phase is a fleeting, but beautiful, and deeply informative chapter in the life of a star. It is a moment of profound and often dramatic transformation, a bridge between the long, quiet stability of the main sequence and the final, brilliant, and often spectacular glory of the giant phase. Betelgeuse, the great crimson jewel of the winter sky, is more than just a beautiful star. It is a cosmic laboratory, a nearby and accessible example of one of the most extreme and most important types of objects in the universe: a red supergiant. Its sheer size, its profound instability, and its impending and spectacular death make it an object of intense and enduring fascination for both professional astronomers and amateur stargazers alike. It is a star that is, in a very real sense, living on borrowed time, and in its slow and often dramatic death throes, it is teaching us a great deal about the life and death of the most massive stars in the cosmos. Betelgeuse is a semi-regular variable star, its brightness changing in a complex and not fully understood rhythm. There seems to be a primary period of about 400 days, which is thought to be related to the fundamental radial pulsation of the star's vast convective envelope. But there are also other longer-term cycles, and a great deal of irregular, chaotic variability superimposed on top of these. This complex variability is a sign of the deep and often violent instabilities that are at play in the heart of this dying giant. In late 2019, Betelgeuse underwent a dramatic and unprecedented dimming event, its brightness dropping by a factor of almost 3. This great dimming sparked a flurry of speculation, both in the scientific community and in the popular press. Was this the prelude to a supernova? Was the demon star finally about to explode? The answer, it turned out, was more subtle, but no less fascinating. High-resolution images from the Hubble Space Telescope and the Very Large Telescope revealed that the dimming was not caused by a change in the star's intrinsic luminosity, but by a vast cloud of dust that had been ejected from the star's surface and was temporarily obscuring our view. Betelgeuse had, in a sense, sneezed. It had undergone a surface mass ejection, a localized and powerful eruption that had flung a huge amount of its own atmospheric material out into space. As this material traveled outwards and cooled, it condensed into a thick cloud of silicate and carbon dust, a temporary and beautiful cosmic veil. This event was a stunning confirmation of a long-held theory that the mass loss from red supergiants is not a smooth, steady process, but is often clumpy, episodic, and driven by the violent, convective, and magnetic activity on the star's surface. The sheer physical size of Betelgeuse is almost impossible to comprehend. Its radius is thought to be about 764 times that of our Sun. This is a number that is so large it almost loses its meaning. But if you were to place Betelgeuse at the center of our solar system, its roiling, crimson surface would extend out past the orbit of the asteroid belt and would be dangerously close to the orbit of Jupiter. It is a star of truly colossal proportions, and yet, for all its size, it is not particularly massive. Its current mass is estimated to be somewhere between 16 and 19 times the mass of our Sun. This means that its average density is incredibly, almost absurdly, low, thousands of times less dense than the air in the room you are in. It is a vast, tenuous, and ghostly behemoth. And it is a young star. In cosmic terms, it is thought to be only about 8 to 8.5 million years old. But because of its immense initial mass, it has burned through its nuclear fuel at a furious pace and has already evolved off the main sequence and into its final red supergiant phase. And it does not have much time left. Astronomers estimate that Betelgeuse will end its life in a spectacular core collapse supernova sometime in the next 100,000 years. When this happens, it will be the astronomical event of a lifetime, and perhaps of a millennium. It will be the closest supernova to Earth to have been observed since the invention of the telescope. At its peak, it will shine with a brightness that could rival that of the full moon, a single, brilliant point of light that will be easily visible in the daytime sky. It will be a spectacular and beautiful final farewell from one of our most beloved and most enigmatic celestial neighbors. And in its death, it will give a final and profound gift to the cosmos. The heavy elements that have been forged in its deep nuclear furnace, the carbon, the oxygen, the silicon, the uranium will be scattered into the interstellar medium, enriching the cosmic gas clouds from which a new generation of stars, of planets, and perhaps of life will one day be born. Betelgeuse is more than just a star. It is a story of life, of death, of transformation, and of the deep, beautiful, and endless cycle of cosmic creation and renewal. The classification of stars into different populations is one of the most fundamental and most powerful organizing principles in modern astronomy. It is a system that allows us to read the history of the universe in the light of the stars themselves. The story begins, as we have seen, with Walter Baade in the 1940s, and his realization that the stars in our galaxy could be divided into two broad categories. Population 1 stars, like our own Sun, are found in the disk of the galaxy. They are relatively young, and they are rich in metals, Population 2 stars, on the other hand, are found in the galaxy's central bulge and its surrounding spherical halo. They are ancient, and they are very poor in metals. This simple observational distinction tells a profound story of cosmic chemical evolution. The universe, in its infancy, was a very simple place, made almost exclusively of the light elements, hydrogen and helium, that were forged in the Big Bang. The very first stars to form in this primordial gas, the hypothetical population 3 stars, were therefore completely metal-free. These stars were likely incredibly massive, and because of their lack of metals, which act as an efficient cooling agent in modern star formation, they were able to grow to sizes that are almost unimaginable today, perhaps hundreds of times the mass of our Sun. And because of their immense mass, they lived incredibly fast and died incredibly young. They're spectacular and often universe-shaping. Lives ending in powerful supernova explosions after only a few million years. It was in the fiery and often violent deaths of these first population 3 stars that the first heavy elements were forged. The carbon, the oxygen, the iron, the silicon, all the elements that are essential for the formation of rocky planets and for the chemistry of life, were created in these primordial stellar furnaces and then scattered into the interstellar medium. The next generation of stars, the population 2 stars, were born from this slightly and beautifully enriched gas. They are the true ancient elders of our galaxy, stars that are over 10 billion years old. They have a low, but non-zero, metal content, a faint chemical echo of the first stars that came before them. And they, in turn, through their own, long and often dramatic, stellar lives, continued this process of cosmic alchemy. As they aged and died, they released even more metals into the surrounding space, further enriching the cosmic gas clouds, and so, with each successive generation of stars, the metal content of the galaxy has steadily increased. Our own population-Y Sun, a relative newcomer to the galactic stage, born a mere 4.6 billion years ago, is the product of this long and patient process of cosmic recycling. Its relatively high metal content, about 1.4% of its total mass, was the essential and non-negotiable prerequisite for the formation of our own solar system. Without the metals from countless generations of long-dead stars, there would be no rocky planets, no Earth, no life, no us. We are, in the most literal and profound sense, the children of the stars, the atoms in our bodies, the iron in our blood, the calcium in our bones, the oxygen we breathe, were all forged in the fiery hearts of stars that lived and died long before our Sun was even born. The search for the elusive. Population 3 stars is one of the great and most challenging quests in modern astronomy. We will likely never see one of these primordial giants directly in our own galaxy. They are all long gone. But we are now, for the first time, with the incredible deep time-seeing power of the James Webb Space Telescope, able to look back to the very edge of the observable universe, to the cosmic dawn, and to search for the faint, red-shifted light of the very first galaxies, the galaxies that were built from and lit up by these first, magnificent, and universe-shaping stars. The life of a star is a delicate and often dramatic balancing act for millions, billions, or even trillions of years. A star is in a state of hydrostatic equilibrium, a beautiful and stable dance between two immense and opposing forces. On the one hand, there is the relentless inward crush of its own gravity, constantly trying to pull all of its matter down into a single, infinitely dense point. On the other hand, there is the powerful outward push of the pressure generated by the nuclear fusion reactions in its hot, dense core. As long as these two forces are in balance, the star is stable, shining with a steady and often life-giving light. But this balance is a temporary one. A star is a finite system with a finite amount of nuclear fuel. And when that fuel begins to run out, the star's long and often peaceful. Life enters its final and often spectacular act. The story of stellar evolution is, at its heart, the story of this battle and of what happens when the fires of fusion begin to flicker and die. All stars are born from the gravitational collapse of vast cold clouds of interstellar gas and dust. As a clump of this material collapses, it heats up, forming a hot, dense, and glowing protostar. As it continues to accrete more material, its core temperature and pressure continue to rise until it reaches a critical threshold of about 10 million degrees Kelvin. At this point, the nuclear furnace ignites. Hydrogen atoms begin to fuse together to form helium, releasing a tremendous amount of energy in the process. This is the birth of a true star. The outward pressure of this new and powerful energy source halts the gravitational collapse, and the star settles into the long, stable, and hydrogen-burning phase of its life, the main sequence. The star's position on the main sequence is determined almost entirely by its initial mass. Low-mass stars, like the red dwarfs, are small, cool, and dim. They burn their hydrogen fuel incredibly slowly and can live for trillions of years. High-mass stars, like the hot blue O-type stars, are large, hot, and incredibly luminous. They burn through their fuel at a furious pace and live for only a few million years. Our own sun, a modest, yellow, G-type star, sits comfortably in the middle, with a main sequence lifetime of about 10 billion years. But eventually, for all stars, the hydrogen fuel in the core runs out, and this is where their evolutionary paths diverge dramatically. For a low-mass star, like our sun, the now inert helium core begins to contract and heat up. Hydrogen fusion ignites in a shell around this core, which causes the star's outer layers to expand and cool. The star becomes a red giant. Eventually, the core becomes hot and dense enough to ignite the fusion of helium into carbon. After this helium-burning phase, the star is not massive enough to ignite the fusion of carbon. Its nuclear life is over. It sheds its outer layers, creating a beautiful, glowing planetary nebula. And its hot, dense, carbon-oxygen core is left behind to slowly cool and fade as a white dwarf. For a high-mass star, the story is far more violent. After the red supergiant phase, its core is massive enough to continue the process of nuclear fusion, creating a series of nested, onion-like shells of heavier and heavier elements: helium, carbon, oxygen, neon, silicon, and finally, iron. The fusion of iron does not release energy, it consumes it. The nuclear furnace has been extinguished. Gravity wins its long and patient battle. The iron core collapses catastrophically in a fraction of a second, triggering a titanic, core collapse supernova explosion that can briefly outshine an entire galaxy. What is left behind is either an incredibly dense neutron star, or, if the progenitor star was massive enough, a black hole, an object whose gravity is so strong that not even light can escape. This is the grand and beautiful cycle of stellar life and death, a cycle that has, over the 14 billion-year history of the universe, transformed the simple, primordial gas of the Big Bang into the rich and complex chemical tapestry that makes up our world and ourselves. When a star like our sun reaches the end of its life, it does not go out with a bang, but with a long, slow, and beautiful sigh. The process begins when the hydrogen fuel in its core is exhausted. The star, no longer able to support itself against the inward crush of its own gravity, begins a series of profound and dramatic transformations. The now inert helium core contracts and heats up. This, in turn, heats the shell of hydrogen that surrounds the core, causing it to ignite and to begin fusing hydrogen into helium at a furious rate. The immense energy released by this shell-burning source pushes the star's outer layers outwards, causing the star to swell to hundreds of times its original size. As it expands, its surface cools, and its color changes from a gentle yellow to a deep and brilliant red. The star has become a red giant. This is the fate that awaits our own sun in about 5 billion years. It will expand to engulf the orbits of Mercury and Venus, and it will likely vaporize the oceans and atmosphere of our own beloved Earth. But the story is not over. As the star continues on its red giant path, the helium core continues to contract and heat up. Eventually, for a star like our Sun, it will reach a temperature of about 100 million Kelvin. At this point, a new and even more powerful nuclear fire is ignited, the fusion of helium into carbon. For a low-mass star, this ignition is a sudden and violent event known as a helium flash. The core is in a strange, degenerate state, and the fusion reaction spreads through it in a matter of hours, releasing a tremendous amount of energy. But this explosion is buried deep within the star's interior, and its effects on the outside are surprisingly gentle. The star contracts, its surface heats up, and it settles into a new, stable phase of its life, the horizontal branch, where it calmly fuses helium in its core for another 100 million years or so. But this, too, is a temporary reprieve. Eventually, the helium in the core is also exhausted, leaving behind an inert core of carbon and oxygen. The star then begins its second ascent up the giant branch, a phase known as the asymptotic giant branch. It is now a truly colossal and deeply unstable object, with two nested fusion shells, an inner helium-burning shell and an outer hydrogen-burning shell. In this final and often turbulent phase, the star undergoes a series of thermal pulses, powerful and often chaotic. Flashes of the helium-burning shell that cause the star to pulsate and to shed its outer layers in a series of powerful stellar winds. Eventually, the entire hydrogen-rich envelope of the star is blown away into space, creating a beautiful, glowing, and often intricate cloud of gas and dust, a planetary nebula. At the center of this expanding and often short-lived cosmic jewel lies the hot and incredibly dense remnant of the star's core, a white dwarf. A white dwarf is a stellar corpse, an object that is no longer generating energy through nuclear fusion. It shines only with its own residual heat, a heat that will take billions and even trillions of years to radiate away. It is an object of incredible density, with the mass of a sun packed into a volume the size of the Earth. A single teaspoon of its material would weigh as much as a truck. It is supported against the final, and otherwise inevitable, crush of gravity by electron degeneracy pressure, a quantum mechanical force that arises from the fact that electrons are fermions and cannot be squeezed into the same quantum state. But even this powerful quantum pressure has its limits. If a white dwarf accretes enough mass from a binary companion to push it over the Chandrasekhar limit of about 1.4 solar masses, it will explode as a spectacular Type Ia supernova. But if it is left to its own devices, it will simply cool, and cool, and cool, until after a time far longer than the current age of the universe, it will become a cold, dark, and eternally silent black dwarf, a final and invisible monument to the long, beautiful, and ultimately gentle life of a sun-like star. The universe, in its grand and often violent unfolding, is a place of almost unimaginable extremes, and nowhere are these extremes more apparent than in the strange, beautiful, and often terrifying objects that are left behind after the death of the most massive stars. When a star with more than about 8 times the mass of our Sun exhausts its nuclear fuel, its iron core collapses catastrophically, triggering a core collapse supernova explosion that can briefly outshine an entire galaxy. But what is left behind in the heart of this cosmic cataclysm? The answer depends on the precise mass of the collapsing core. If the core is not too massive, typically less than about 2 to 3 times the mass of our Sun, the collapse will be halted by neutron degeneracy pressure. This is a quantum mechanical force, similar to the electron degeneracy pressure that supports a white dwarf, but much, much stronger. The immense pressure in the collapsing core is so great that it forces the electrons to merge with the protons, creating a super-dense ball of almost pure neutrons. This is a neutron star. It is an object of almost unbelievable density. It packs the mass of 1.5 suns into a sphere that is only about 20 kilometers in diameter, the size of a large city. A single, sugar cube-sized piece of neutron star material would weigh as much as all of humanity combined. The gravitational pull at its surface is hundreds of billions of times stronger than that of the Earth. And as the progenitor star's core collapses, the conservation of angular momentum causes the neutron star to spin at an incredible rate, often hundreds of times per second. This rapid rotation, combined with the star's incredibly strong magnetic field, can turn the neutron star into a pulsar, a cosmic lighthouse that sweeps 2 powerful beams of radiation across the galaxy. But if the collapsing core is even more massive, if it exceeds the Tolman-Oppenheimer-Volkoff limit of about 2 to 3 solar masses, then not even the immense and almost incompressible force of neutron degeneracy pressure can halt the final and otherwise inevitable gravitational collapse. The core continues to shrink, its density and its gravitational pull increasing without limit, until it crushes itself into a black hole, an object whose gravity is so strong that it warps the very fabric of space-time around it into a one-way membrane, an event horizon from which nothing, not even light itself, can escape. The existence of black holes is one of the most profound and most beautiful predictions of Einstein's general theory of relativity, and it is a prediction that has now been confirmed with a wealth of observational evidence, from the dance of the stars that orbit the supermassive black hole at the center of our own galaxy, to the direct detection of the gravitational waves that are emitted when 2 black holes collide and merge. The interior of a black hole is a realm where our current laws of physics break down. General relativity predicts a singularity at its center, a point of infinite density and infinite space-time curvature. But this is almost certainly a sign that the theory is incomplete. A full theory of quantum gravity is needed to understand what truly happens at the heart of a black hole. But what we do know is that a black hole is a final and absolute end state. It is a cosmic prison, a place where matter, energy, and information are seemingly lost to the outside universe forever. The story of stellar remnants, of white dwarfs, of neutron stars, of black holes, is a story that is told in the language of the most extreme physics imaginable. It is a story of quantum mechanics, of general relativity, of nuclear physics, of gravity pushed to its absolute limits, and it is a story that is still being written. The details of the supernova explosion mechanism, the precise dividing lines between the different possible end states, the nature of the matter in the core of a neutron star, these are all active and exciting areas of research, but the broad outlines of the story are clear. And it is a story that is crucial to our own existence, for it is in the fiery and often violent, deaths of the most massive stars that the heavy elements that make up our world, and ourselves, are forged and scattered into the cosmos. We are, in the most literal sense, the children of supernova, the recycled ashes of long-dead stars, given a second and far more beautiful life. In the vast and often imaginary Cosmic Hall of Fame, a special place of honor must be reserved for the true heavyweight champions of the stellar kingdom, the colossal and often enigmatic stars that are known to astronomers as the red supergiants. And among these, one star in particular has long held the title of the biggest, the baddest, and the most mysterious of them all, the behemoth, WOH G64. This is not just a big star, it is a star of almost mythological proportions, a star that seems to be actively and gleefully breaking the very rules that are supposed to govern the lives of stars. It is a star that is located not in our own familiar Milky Way, but in our nearest and much wilder galactic neighbor. The Large Magellanic Cloud, WOH G64, was first identified in the 1970s by a trio of astronomers, Westerlund, Olander, and Hesser, whose names are now immortalized in the star's official designation. And from the very beginning, it was clear that this was not an ordinary star. Its immense size and its incredible brightness were immediately apparent. Modern estimates suggest that its radius is about 1,540 times that of our Sun. This is a number that is difficult to wrap the human mind around. But if you were to replace our Sun with WOH G64, its fiery and bloated surface would extend out past the orbit of Jupiter, engulfing all of the inner rocky planets and the asteroid belt in a single fiery gulp. And its luminosity is no less staggering. It is thought to be shining with the light of about 280,000 suns, making it one of the most luminous, cool supergiants known. But for all its brilliance, we cannot see this star with our own eyes. It is shrouded in a thick and often impenetrable cocoon of gas and dust, a toroidal or donut-shaped nebula that it has itself created. This dusty veil is a telltale sign that WOH G64 is a star in the final and most turbulent stages of its life. It is actively and violently shedding its outer layers, blowing them off into space in a powerful and often chaotic stellar wind. This circumstellar material, which extends for over a light year from the star, is a testament to the profound instabilities that are at play in the heart of this dying giant. And here is where the story gets even stranger. For a star of its immense size and luminosity, WOH G64 is surprisingly, and almost impossibly, cool. Its surface temperature is only about 3,400 Kelvin. This places it in the realm of the red supergiants, but it also places it at, or even beyond, the Hayashi limit, a theoretical boundary on the HR diagram to the right of which a star of a given mass cannot exist in a state of stable hydrostatic equilibrium. WOH G66 is, in a very real sense, a star that should not exist. This has led to a number of fascinating and often speculative theories. Is it really a single star, or could it be a close, and as yet unresolved, binary system, with a more massive and hotter companion star that is hidden from our view? The presence of a companion could help to explain the star's extreme mass loss, its unusual chemistry, and its location in a seemingly forbidden region of the HR diagram. Or is it something else entirely? Could it be a Thorne-Zhitkov object, a bizarre and still hypothetical type of star where a neutron star has been swallowed by and has spiraled into the core of a red supergiant? The physics of such an object would be incredibly complex, and it could, in principle, lead to the kind of extreme luminosity and instability that we see in WOHG 64. The location of the behemoth, in the metal-poor environment of the Large Magellanic Cloud, is another crucial clue. The lower abundance of heavy elements in the LMC is thought to allow stars to grow to much larger masses and sizes than they can in our own, more metal-rich Milky Way. WOHG 64 may be a living and soon to be dying example of the kind of primordial, monster stars that were common in the early and much wilder days of the universe. It is a cosmic fossil, a window into a time when the universe was a more extreme and more creative place. WOHG 64 is more than just a big star. It is a puzzle, a paradox, and a profound mystery. It is a star that is challenging our most basic and most cherished models of stellar evolution, and in its strange, beautiful, and ultimately self-destructive glory. It is a powerful reminder that the universe is still full of surprises, and that the true cosmic monsters are often far stranger and far more magnificent than anything we could have ever imagined. We build rockets, sending probes to the farthest corners of our solar system. We gaze deep into space with telescopes that can reveal the faint, ancient light of galaxies billions of light years away. Our technology is powerful, a testament to the relentless reach of the human mind. Our curiosity is boundless, an insatiable hunger to understand the grand, the cosmic stage upon which our fleeting lives unfold. And yet, for all our progress, for all our ambition, there are places we can never reach. There are realms so distant, so fundamentally inaccessible, that they will forever remain a mystery, shrouded in the darkness of the ultimate unknown. These are the forbidden zones of the universe, regions of reality that are lost to us, not because of a failure of our technology, but because of the very nature of the cosmos itself. Some of these forbidden realms are being actively created right now, as we speak, torn from our view by the relentless and accelerating expansion of the cosmos. Entire galaxies, once our cosmic neighbors, are receding from us at speeds faster than the speed of light, slipping silently and irrevocably beyond the horizon of what is possible for us to ever see or to touch. Others of these forbidden zones are buried deep within the most extreme and violent objects in the universe, in the hearts of black holes. Their event horizons are not just boundaries, they are one-way membranes in the fabric of space-time, a point of no return that seals away whatever falls inside, its secrets, its information, its very existence, forever erased from our view. And some of these forbidden realms exist not in space, but in time. The very first moments of the universe's creation, the fiery crucible of the Big Bang, are hidden from us behind a veil of such extreme heat and density that no telescope, no theory, no future breakthrough will ever be able to pierce it. And yet, we wonder, we imagine. We reach with our minds where our bodies and our machines can never go. Could those distant, unreachable galaxies, forever cut off from us by the expanding void, harbor their own unique forms of life, their own civilizations, forever living in their own isolated cosmic island? Forever unaware of our existence, do the dark, silent hearts of black holes conceal the deep, fundamental secrets of the nature of reality itself? The answers to the puzzle of quantum gravity is the true story of the birth of time, of the very beginning of our universe, locked away behind an impenetrable and eternal cosmic curtain. The forbidden zones of the universe are a profound and humbling reminder of our own inherent limits, but they are also a powerful and beautiful testament to our greatest strength, our curiosity. Even in the face of the unreachable, of the unknowable, of the eternal mystery, We continue to ask, to explore, to dream, and perhaps, in doing so, in the very act of reaching for what lies beyond our grasp, we find something just as profound and just as meaningful as the answers we seek. The universe is vast, far vaster than our human eyes, or even our most powerful and sophisticated telescopes, can ever hope to see when we gaze up at the clear, dark expanse of the night sky. We are not just looking out into space, we are looking back in time. The light from the nearest stars has traveled for years to reach us. The light from the Andromeda Galaxy, our closest major galactic neighbor, has been on its journey for over 2.5 million years. And the faint, distant smudges of light from the most remote galaxies have been traveling towards us for billions of years, carrying with them a ghostly image of the universe in its infancy. But there is a limit, a fundamental and absolute boundary to our vision. There is a cosmic horizon, a spherical shell around us, beyond which we can never see, never explore, and never reach. This is the cosmic censorship zone, the vast and perhaps infinite region of the cosmos that exists beyond the confines of our observable universe, a realm where reality itself becomes, for us, forever unknowable. Our observable universe, the part of the cosmos from which light has had time to reach us since the Big Bang, stretches out for about 46 billion light-years in all directions. This number might seem strange. If the universe is only 13.8 billion years old, shouldn't we only be able to see objects that are at most 13.8 billion light-years away? The reason we can see farther is because the very fabric of space itself has been expanding throughout the entire history of the universe. The distant galaxies that emitted the light we see today were much closer to us when that light began its long journey. But in the billions of years that it has taken for that light to travel to us, the space between us and those galaxies has been stretching, carrying them much farther away. This expansion of space also stretches the wavelength of the light itself, a phenomenon known as cosmic redshift. The light from the most distant galaxies is so severely redshifted that it has been stretched from the visible and ultraviolet parts of the spectrum all the way into the infrared and microwave regions, which is why we need specialized telescopes like the James Webb Space Telescope to see it. But there is a profound and deeply unsettling problem with this cosmic expansion. It is not slowing down, as one might expect due to the mutual gravitational pull of all the matter in the universe. It is accelerating, driven by a mysterious and still completely unexplained, repulsive force known as dark energy. The universe is not just growing, it is growing at an ever-increasing rate. This has a dramatic and inescapable consequence. As time passes, more and more of the distant galaxies are being pushed away from us so fast that they will eventually cross our cosmic event horizon. They will be receding from us at a speed that is faster than the speed of light itself. This does not violate Einstein's theory of relativity, as it is space itself that is expanding, not the galaxies moving through space. But it does mean that any light emitted by those galaxies after they cross this horizon will never be able to reach us. They will be, in a very real sense, causally disconnected from our future. Anything that is currently beyond 46 billion light-years from us is already forever lost. And the galaxies that are currently on the edge of our observable universe will one by one follow them into the darkness, their light fading from our view, their existence erased from our cosmic reality. This is not a temporary technological problem. It is a fundamental, physical limit. Even if humanity one day masters the art of interstellar, or even intergalactic travel, even if we create spacecraft that can approach the speed of light, we will still never be able to reach these hidden, forbidden regions. The very laws of physics, the relentless, accelerating expansion of space-time itself, prevent us. This leads to one of the most profound and most tantalizing questions in all of cosmology: what lies beyond the observable universe? The simplest and most conservative answer is based on the cosmological principle, the assumption that our corner of the universe is not special, and that on the largest scales, the cosmos is homogeneous and isotropic, meaning it looks roughly the same everywhere and in all directions. If this is the case, then the universe beyond our view is likely just more of the same. An endless, and perhaps infinite, expanse of space filled with the same kinds of galaxies, stars, and planets, all governed by the same universal laws of physics. In this picture, the universe beyond our horizon is not fundamentally different from our own. It is just forever inaccessible. But there are other, more exotic and more mind-bending possibilities. Some cosmologists, working on the frontiers of theoretical physics, suggest that beyond our observable universe, the very nature of reality might be different. If the Big Bang was not a single, unique event, but was just one of many in a larger, eternal inflation process, then the universe beyond our sight could be a vast and chaotic multiverse. There could be other bubble universes, each with its own unique set of physical laws, fundamental constants, and even different numbers of dimensions. These would be separate, parallel pockets of reality, forever cut off from our own, each one a different and perhaps wildly different answer to the question of what a universe can be. The question of whether our own universe is finite or infinite also has a profound bearing on what might lie beyond our horizon. If the universe is truly spatially infinite, as the current data seems to suggest, then the consequences are staggering. In an infinite universe, every possible arrangement of particles, every possible configuration of matter and energy must, by statistical necessity, repeat itself an infinite number of times. This means that somewhere out there, far, far beyond the cosmic censorship zone, there is another Earth, another you, an almost identical copy, living out an almost identical life, perhaps making just one tiny, different choice at this very moment. And there are an infinite number of such doppelgangers, spread out across an infinite cosmic tapestry. If, on the other hand, the universe is finite, then it might have a strange and wonderful topology, wrapping around on itself in a higher dimension. In such a universe, if you were to travel far enough in one direction, you might eventually end up right back where you started, like an ancient mariner circumnavigating the surface of a spherical Earth. And then there is the most radical and least likely possibility that beyond our universe, there is simply nothing, a true absolute void, a region where even space and time themselves cease to exist. This idea, however, contradicts much of what we have learned from quantum mechanics, which suggests that even the emptiest of space is a seething, energetic sea of quantum fluctuations. What makes the cosmic censorship zone so eerie and so philosophically profound is that we will likely never know for sure what lies beyond it. And as the universe continues its accelerating expansion, the region of space that we can access, the volume of our observable universe, is in a relative sense shrinking. The galaxies that we can see today, the most distant quasars and the most ancient protogalaxies, will eventually fade from our view, their light stretched by the expanding space into an undetectable, infinite redshift. Billions, and then trillions, of years from now. Future observers in our own local group of galaxies will look up at a sky that is almost completely dark, empty, and devoid of the rich cosmic tapestry that we are privileged to still be able to see. The grand cosmic web of galaxies will have vanished into the darkness, leaving only a small, lonely, and gravitationally bound island of stars in an infinite and seemingly empty void. the knowledge that we have so painstakingly acquired, the knowledge that we live in a vast, expanding cosmos filled with billions of other galaxies, could one day be lost, buried in the digital archives of a long-forgotten history, with no way for a future civilization to ever independently verify it. And yet, even within these profound and humbling limitations, our universe holds endless mysteries. The cosmic censorship zone is not just a physical boundary, it is a philosophical one. It is a stark and powerful reminder of the inherent limits of human knowledge. It tells us that no matter how far we look, no matter how powerful our instruments become, there will always be something just beyond our reach, some deeper and perhaps ultimate truth that we can never fully grasp. It is the final and most absolute cosmic horizon, a frontier that can never be crossed, not because we lack the technology or the will, but because the very nature of our expanding and accelerating. Reality ensures that some of its deepest secrets will forever remain hidden from our view. This is a humbling realization. We are used to thinking of science as a powerful and perhaps even omnipotent tool. A tool that can, in principle, unlock all the mysteries of the universe. But the very nature of the cosmos itself seems to be telling us that some answers will always and forever be out of our reach. This does not mean that we should stop searching. On the contrary, it makes our quest for knowledge all the more precious, all the more urgent. Every moment that we have to study the cosmos, every single photon of ancient light that we can gather, is a fleeting and irreplaceable opportunity to piece together the story of our universe before it moves, forever beyond our grasp. In the end, the cosmic censorship zone is not just a physical limit, it is an existential one. It forces us to confront our own, small, and temporary place in an endless and endlessly shifting reality. It reminds us that there will always be things we cannot know, places we cannot visit, and mysteries we cannot solve. But perhaps, in the end, that is what makes the journey of exploration so beautiful and so profoundly human. The universe is not a puzzle for us to solve, but a poem for us to wonder at, a story for us to participate in, even as its most distant and most ancient. Chapters are slowly and inexorably drifting further and further away from our reach. The universe is a time machine. This is not a poetic metaphor. It is a literal, physical fact. Every time we look up at the night sky, we are not seeing the cosmos as it is in our present moment, but as it was in a distant and often ancient past. The farther away a galaxy is, the longer its light has taken to travel to us. And therefore, the further back in time we are looking. The light from some of the most distant galaxies has been journeying towards us for billions of years, carrying with it a ghostly, and often beautiful, image of the universe in its infancy. And here lies one of the most haunting and most profound truths about our cosmos. Some of the galaxies that we observe in the night sky, some of the very objects that we are studying with our most powerful telescopes, no longer exist. They are phantoms, cosmic ghosts, whose last dying light is only just now reaching our shores, while they themselves have already vanished. Their substance scattered, their stars extinguished, their reality dissolved into the expanding void. This eerie and deeply counterintuitive phenomenon is a direct consequence of the universe's rapid and accelerating expansion. The very fabric of space itself is stretching, and it is carrying the distant galaxies along with it, pushing them ever farther apart. For the galaxies that are relatively close to us, in our own local cosmic neighborhood, this expansion is a slow and gentle process. But for the galaxies that lie at the extreme, outer edges of our observable universe, The expansion is happening so quickly that they are, in effect, being pulled out of our reality. Their light struggling against a cosmic current that is flowing faster than the speed of light itself. This means that while we can still see the light that they emitted billions of years ago, a message from their distant past, they themselves have already crossed our cosmic event horizon, the point of no return, the boundary beyond which no new information, not a single additional photon of light, can ever reach us again. To truly grasp this strange and wonderful idea, imagine you are standing on the shore of a vast ocean, watching a boat sail away towards the horizon. As it moves farther and farther away, it will eventually reach a point where it seems to disappear from your view, not because it has ceased to exist, but because the curvature of the earth has carried it beyond the limit of your sight. Now, replace the ocean with the expanding fabric of space, and the boat with an entire galaxy. The universe is stretching so rapidly that certain very distant galaxies have already been carried beyond our cosmic horizon, never to be seen again in their present state. Their ancient light is still traveling towards us, a long and fading echo from their past. But once that final ancient light has all arrived, no more will follow. They will fade from our view, not because they have become too dim, but because they have become too distant, their light forever trapped in a space-time that is expanding too fast for it to ever reach us again. The most astonishing and most humbling aspect of this phenomenon is that there are galaxies we can see today, right now, in the images from our most powerful telescopes that have, in all likelihood, already ceased to exist in any recognizable form. Some of them may have been swallowed by supermassive black holes. Others might have been torn apart in colossal galactic collisions, and many have simply been stretched out into a thin, cold, and featureless nothingness by the relentless and accelerating expansion of space. The beautiful spiral arms, the glittering, star-forming nebulae, the vast, ordered structures that we see in these ancient images, all of this is long gone. The light that we receive from them today is their final message, their last beautiful glimpse into a vibrant existence before they vanished forever from the stage of the cosmos. One of the most famous and iconic images in the history of astronomy, the Hubble Deep Field, is a perfect illustration of this. This single, long-exposure image captured the light of thousands of distant, and therefore ancient, galaxies in a tiny, seemingly empty, patch of the night sky. Many of these galaxies are so far away that their light has been traveling for over 10 billion years to reach us. We are seeing them as they were when the universe was in its infancy, just a few 100 million years old. And yet, they are no longer there. The specific cosmic structures that they formed, the individual stars that they contained, and perhaps even the planets and the potential life that may have orbited within them, all of this is gone, washed away by the relentless cosmic tide of time and expansion. But their light, like a faint, beautiful echo from a long-forgotten past, is only just now reaching us, allowing us to witness them as they were, frozen forever in a single, ancient moment of time. This is a concept that is deeply difficult for our minds to wrap themselves around, because in our everyday terrestrial experience, things do not just disappear like this. When we look at an object, a tree, or a house, we have a very strong and reliable intuition that it exists, here and now, in our present moment. But the universe, on its grandest scales, does not work that way. The farther away something is, the older the image we see of it. And for the most extremely distant galaxies, we are looking so far back in time that their present state is not just unknown to us, it is in a very real sense, unknowable. Some of them may still exist, in some transformed and evolved form, but many others are simply gone. Their matter dispersed, their energy absorbed, their story concluded in the vast, silent expanse of space. What makes this cosmic vanishing act even more unsettling is that the universe's accelerating expansion is, as far as we know, an irreversible process. The galaxies that are currently teetering on the very edge of our observable universe today will, one by one, soon be lost to us forever. We will still be able to see their ancient, fading light for a while, for perhaps millions or even billions of years to come. But that light, that final ghostly message from their past, will eventually stop arriving. They will fade into a final, absolute blackness. Not because they have been destroyed in a fiery cataclysm, but because the fundamental laws of physics, the very geometry of our expanding space-time, will have made it impossible for their photons to ever reach us again. The fabric of space will have stretched so much and so quickly that they will have been, in effect, completely and irrevocably erased from our reality. This means that, in a very real sense, we are living in a golden age of cosmic observation, right now. At this specific and perhaps fleeting moment in cosmic history, we have the technology to look deep into space and to see the beautiful, ghostly remnants of these ancient phantom galaxies. But in the far, far future, observers in our own galaxy will look up at a much, much lonelier universe. The distant galaxies that we marvel at today will no longer be visible. The Milky Way and its small, gravitationally bound group of neighboring galaxies will be all that remains in sight. And future astronomers, future civilizations, might never even know that the billions of other galaxies that we can still see ever existed. The record of their existence will have been lost, their light no longer able to reach us, their story erased by the expanding void. But this does not mean that these phantom galaxies are meaningless. Even though they have disappeared from the present-day universe, their ancient, ghostly light tells us a story, a crucial and irreplaceable story of the early cosmos. A story of how the first stars and galaxies formed from the primordial soup of the Big Bang. A story of how the intricate, beautiful, and complex structures of the universe evolved over billions of years. Every single ancient photon that reaches the mirror of our telescopes is a precious message from the past, a faint, beautiful whisper from a galaxy that may have been long, long gone. And these photons are precious because they allow us to piece together the history of our universe, before that history itself is lost to the inexorable forward march of time. There is also a profound and deeply human philosophical question that is hidden within this strange, cosmic reality. If we see something, but it no longer exists, did it ever really exist in the way that we intuitively understand existence? When we look at a galaxy that is 10 billion light-years away, we are seeing it as it was 10 billion years ago. But if we could somehow, magically, teleport ourselves to that location in space, right now, in our present moment, we would, in all likelihood, find nothing. The stars would be gone. The beautiful spiral structures would have changed beyond all recognition. We would be staring into an empty, dark space, or at something entirely different from what we had expected. This profound disconnect between the past image and the present reality challenges our very understanding of what the now really means. In a universe where time and space are so deeply and inextricably connected, it also raises another, equally unsettling question. How much of our own universe, our own cosmic neighborhood, has already disappeared from the view of a distant, alien observer? Just as we see the ancient, ghostly images of galaxies that no longer exist, it is entirely possible that there are other civilizations, in other distant parts of the cosmos that are, at this very moment, looking back at our own Milky Way, but seeing it as it was billions of years ago. To them, our galaxy, our sun, our Earth, might be nothing more than a faint, ancient glimmer of light from a time long past, a beautiful and poignant relic of a universe that has already moved on without us. One day, we too, in all our complexity and our beauty, may become a phantom, a galaxy whose ancient light continues to travel outwards into the expanding void, a message in a bottle cast into a cosmic ocean. Long after we ourselves have faded from existence, the universe is a vast and endlessly mysterious place. And the phantom galaxies that haunt the lenses of our telescopes are a powerful and beautiful reminder that nothing is permanent. Everything we see, everything we know, everything we are, is temporary, a fleeting, flickering moment in the grand, and often tragic, sweep of cosmic history. And yet, in that fleeting moment, there is a profound and undeniable beauty. The very knowledge that we are witnessing something that no longer exists, something that has been lost to the relentless, cosmic tide, makes every image, every observation, every single precious photon of ancient light all the more meaningful. It reminds us that the universe is always changing, always evolving, and that we are incredibly, wonderfully, and perhaps even tragically lucky to be here, now, to glimpse even the tiniest fraction of its magnificent and ultimately fleeting story. Before it, too, fades forever, beyond our reach. The universe hides its deepest and strangest mysteries in the darkness. And among the most enigmatic of these dark mysteries is the idea of primordial black holes, hypothetical and ghostly, remnants from the very first, fiery moments after the Big Bang. If they exist, they are not like the black holes we know, the stellar mass behemoths that are formed from the violent, explosive deaths of massive stars. These would be something entirely different, something more ancient, more fundamental, more elusive. They would be black holes formed not from the collapse of pre-existing matter, but from the raw, untamed, and incredibly dense energy fluctuations of the newborn universe itself. But here lies the profound and deeply frustrating paradox of their existence if they are real. They are so small, so dark, and so perfectly hidden in the vast, expanding fabric of space that we may never, ever be able to find them. Primordial black holes are believed to have formed in the very first, infinitesimal fractions of a second after the universe came into existence. At that time, the cosmos was an unimaginably hot and dense place, a chaotic, roiling sea of pure energy and fundamental particles. In this primordial soup, tiny, random, quantum fluctuations slight and unavoidable. Imbalances in the density of energy could have been so extreme that they caused certain super-dense regions of space to spontaneously collapse in on themselves, forming minuscule black holes. Unlike the black holes that are formed from the collapse of dying stars, which must have a mass of at least a few times that of our sun, these primordial black holes could, in theory, have any mass. They could be as small as a single atom, or as massive as a large planet, their size depending entirely on the scale and the intensity of the density fluctuation from which they were born. Theoretically, these ancient primordial black holes could have survived for the entire 14 billion-year history of the universe, drifting silently and invisibly through the cosmos. Perfect, dark relics of the first moment of creation. But their very nature, their small size, and their lack of any significant interaction with their surroundings makes them nearly impossible to detect. Unlike the stellar mass or supermassive black holes that we can observe, which are often surrounded by bright, glowing accretion disks of gas and dust that is being pulled into them, these primordial black holes would be, for the most part, completely isolated. wandering through the vast, empty voids of the universe like silent, cosmic ghosts. If they are small enough, they would slowly emit a faint thermal radiation, a process known as Hawking radiation, and would, over immense cosmological timescales, eventually evaporate completely. But if they are just a little larger, say with the mass of a small asteroid, they could persist indefinitely, their existence completely invisible to our current, and perhaps any future, technology. For decades, scientists have been searching for any evidence, however indirect, of these ancient, primordial black holes, but finding them is like looking for a single dark grain of sand in an infinite dark desert. They do not emit any detectable light. They do not interact with their surroundings in any obvious way. And they may be far too small to have any significant gravitational influence on the stars and galaxies around them. The only real hope of detecting them lies in their potential. Gravitational effects. They could, in theory, act as gravitational lenses, their tiny but intense gravity bending the light of a distant star as they pass in front of it, creating a brief and characteristic brightening event. Or they could subtly affect the movement of the large-scale cosmic structures that we can observe. But even these potential clues are incredibly faint, almost imperceptibly so, when set against the vast and often noisy backdrop of the cosmos. One of the most intriguing and most exciting ideas about primordial black holes is that they could be a leading candidate for the mysterious and still completely unidentified dark matter, the invisible gravitational substance that seems to make up the vast majority of the matter in the universe. Dark matter is known to us only through its gravitational influence. It has weight, it pulls on galaxies, it shapes the large-scale structure of the cosmos, but it emits no light, no radiation, no signal of any kind. Could it be that this hidden gravitational mass that has eluded scientists for so long is, in fact, a vast cosmic population of ancient, primordial black holes? Some researchers believe that this is a real and even a likely possibility, but there is, as yet, no direct experimental evidence to support it. If primordial black holes are indeed the source of dark matter, then they are even more elusive and more profoundly mysterious than we ever imagined. They would be everywhere, all around us, making up the very gravitational scaffolding of our own galaxy. And yet, they would remain completely and utterly unseen. The frustrating and beautiful reality is that even if they do exist, we may never be able to definitively prove it. They are too small to be observed directly. They are too dark to emit any detectable radiation. And they are too isolated to reveal themselves through their interactions with the world we can see. Even our most advanced telescopes and our most sensitive gravitational wave detectors may not be enough to ever confirm their presence. We might only ever be able to infer their existence from a collection of subtle, indirect clues, a slight, unexplained anomaly in the motion of a distant galaxy, a brief and unrepeatable flash of lensed light from a background star, a tiny and statistically ambiguous distortion in the faint, ancient glow of the cosmic microwave background. There is a cruel and beautiful irony in this. The very nature of primordial black holes, their ancient origin and their profound physical simplicity, makes them one of the most compelling and most elegant ideas in all of modern physics. And yet, at the very same time, it may place them forever beyond the reach of our direct, empirical verification. They could be everywhere, hidden in the silent, dark void of space. And yet, we might never be able to prove that they are real. The universe, it seems, does not always reveal its secrets easily, some of its deepest and most fundamental. Questions may remain forever unanswered, not because they have no answers, but because the answers are too well, and too perfectly, hidden for us to ever find them. And yet, the possibility of primordial black holes, the dream of finding these ancient cosmic relics, continues to haunt us, to inspire us, to push us forward in our quest for understanding. If they do exist, then they are the oldest and most fundamental structures in the entire universe, predating the formation of galaxies, of stars, and even of the first stable atoms. They are living, breathing fossils from a time before anything we would recognize as existence had even begun. And if they do not exist, then we are left with another, equally profound, mystery. What happened to the extreme, primordial density fluctuations that our theories predict should have formed them? Why did the early universe evolve in such a way that it so perfectly and so elegantly avoided their creation? Either way, whether they are out there in the darkness or not, the search for primordial black holes forces us to confront the very limits of what we can know, of what we can see, of what we can ever hope to understand. The universe is vast, and some of its deepest and most beautiful secrets may remain hidden from us forever, lost in the deep, profound, and eternal silence of space. The solar system that we see today, with its familiar and largely stable arrangement of planets and moons, is a product of billions of years of cosmic evolution. It is a system that has been shaped by violent collisions, by graceful planetary migrations, and by the relentless and patient pull of gravity. When we look up at the familiar, comforting face of our own moon in the night sky, or when we observe the beautiful, intricate dance of the moons of Jupiter and Saturn through our telescopes, we are only seeing a small and perhaps fortunate fraction of what once existed. The solar system was not always as it is now. It was once a far more chaotic, more dynamic, and more violent place, a place where countless, and now forgotten, moons were formed, only to be torn apart, to be ejected into the cold, deep space, or to be lost forever to the dark and silent void. These lost moons, these ghostly and often tragic remnants of a time when our solar system was still young, wild, and unstable, may still exist somewhere out there, hidden beyond the reach of our current instruments, drifting alone and silently in the eternal darkness. Some of them may have been completely destroyed in violent and cataclysmic impacts, their shattered remains now forming the rings of the giant planets or the scattered debris of the asteroid fields. Others may have been thrown out into the distant and largely unexplored reaches of the Oort cloud, a vast, spherical, and icy region that marks the very edge of our solar system, a place where they would remain frozen, undisturbed, and nearly impossible for us to ever detect. And some, the most unfortunate of all, may have escaped the gravitational pull of our sun entirely, becoming rogue moons, wandering aimlessly and eternally through the vast, cold, and lonely expanse of interstellar space, untethered from any star, and destined to drift forever in the endless silent night. In the earliest days of our solar system, more than 4.5 billion years ago, there were no clearly defined planets, no stable, predictable orbits, no familiar cosmic clockwork. Instead, there was a vast, swirling, and turbulent disk of gas, dust, and debris surrounding our young, and still forming, sun. And as this primordial material slowly began to clump together under the influence of gravity, the first infant planets, the protoplanets, and their first nascent moons began to form. But this was not a peaceful or a gentle process. It was a time of cosmic violence, a time of immense and often world-shattering collisions. Newly formed planets and moons were constantly smashing into each other, their surfaces being reshaped, their orbits being altered, or their very existence being snuffed out in a final, fiery instant. Some of these impacts were so powerful, so cataclysmic, that they changed the entire course of our solar system's history. The very moon that we see in our sky today is thought to have been formed from just such an event, a massive and glancing collision between the early, molten Earth and a Mars-sized protoplanetary body. An impact that would have ejected a vast cloud of molten rock and debris into orbit, which then, over time, coalesced to form our familiar and beautiful lunar companion. And if this could happen to our own Earth, then it is almost certain that the other planets in our solar system also had a long and often violent history of moon formation, a history where moons were formed, were destroyed, and were replaced multiple times throughout the chaotic youth of our cosmic neighborhood. The giant, gas planets of our outer solar system, Jupiter and Saturn, have dozens of moons today, a beautiful and complex family of orbiting worlds. But in the distant past, they may have had even more. These gas giants are so incredibly massive that they have a powerful gravitational reach, an ability to capture passing objects and to pull them into orbit. This means that many of their current moons were likely not formed alongside them, but were stolen from the asteroid belt, or were captured from the icy debris of the outer solar system. But just as these giant planets can capture new moons, they can also lose their old ones. When planets migrate, when they slowly shift their positions in the solar system due to the complex gravitational interactions between them, they can disrupt everything around them. A moon that was once in a safe and stable orbit can suddenly find itself on a new and highly elliptical path. A path that could lead it to collide with another moon, to crash into its host planet, or to be flung with immense force out of the planetary system entirely. Jupiter and Saturn, our solar system's two gravitational behemoths, likely underwent significant periods of migration in their early histories. A chaotic, cosmic dance that would have reshaped the entire architecture of the outer solar system, and would have, in all likelihood, resulted in many of their original primordial moons being lost in the process. Some of these lost, ancient moons may still be out there, hiding in the farthest and coldest reaches of our solar system, far beyond the orbit of Neptune, beyond the Kuiper Belt, in the vast and largely mysterious realm of the Oort cloud. The Oort cloud is a hypothetical and almost unimaginably large, spherical cloud of icy bodies that is thought to surround our solar system, at a distance of nearly a light-year from the Sun. It is believed to be the ancient and largely undisturbed reservoir of long-period comets, those icy and beautiful visitors that occasionally get nudged from their distant orbits and fall inwards towards the Sun, their long, ghostly tails of fleeting and beautiful, reminder of the vast, cold, and ancient history of our cosmic home. And if these smaller, icy bodies, these comets, can survive in the Oort cloud for billions of years, then it is entirely possible that some of our solar system's lost ancient moons also ended up there, trapped forever in the faint, gravitational influence of our Sun, but too far away, too cold, and too dark for us to ever see them. These would be frozen and lifeless worlds, locked in the deep, silent space of the outer solar system, their surfaces preserving a perfect and eternally unchanging record of the violent and chaotic youth of our cosmic neighborhood. And even if they do exist, finding them would be a task of almost unimaginable difficulty. They would be too dark and too distant to be observed directly with any of our current or even near-future telescopes. Other, and perhaps more numerous, of these lost moons may have faced an even more dramatic and more final, fate complete, and total ejection from the solar system itself, If a moon, during a close gravitational encounter with a massive planet, was thrown outwards with enough force, with enough velocity, it could have escaped the gravitational pull of our sun entirely, becoming a rogue object, a lonely and untethered wanderer, drifting freely and silently through the vast, dark, and empty expanse of interstellar space. Scientists in recent years have already discovered the existence of rogue planets, planets that do not orbit any star, but instead move, dark and alone, through the galaxy. And if rogue planets exist, then it is almost certain that rogue moons must also exist. Some of them may have been born in the turbulent, star-forming nurseries of our galaxy, but many of them, perhaps even billions of them, may have once been a part of a solar system just like our own, a moon that was torn from its home by the chaotic, gravitational dance of its planetary siblings. And some of them, it is almost certain, may have once been our own, forgotten and long lost, cosmic neighbors, without a nearby star to warm them, to illuminate them. These lost, rogue moons would be almost completely invisible, impossible to detect with even our most advanced and most powerful telescopes. They could pass by other solar systems, moving silently and darkly through the void, never to be captured by the gravity of another planet, forever alone in the endless cosmic night. And if any of these moons once had the potential for life, if they had subsurface oceans of liquid water, or the right chemical ingredients for biology, their ejection into the cold, deep space would have sealed their fate. Without the gentle, life-giving warmth of a star, any potential for life would have been frozen in an instant, preserved forever in the deep, icy shell of a moon that would never again see the light of day. The thought of such worlds, of places that once held the potential for oceans, for weather, for dynamic, geological activity, now drifting, dark and aimlessly, through the vast and lonely void, is a profound and deeply haunting reminder of just how fragile and how precious celestial bodies can be. Unlike the massive planets, which have a strong and stable gravitational hold on their orbits, the smaller moons are far more easily lost, making them some of the most transient and most vulnerable objects in the entire universe. The lost moons of our early solar system are not just a romantic and tragic relic of our cosmic past. They are also a crucial and largely missing piece of the puzzle of how planetary systems form and evolve. By studying the moons that remain, the ones that have survived the long and often violent history of our solar system, scientists can begin to infer what might have happened to those that were lost. The deep, ancient craters on our own moon, the irregular and often chaotic shapes of the asteroid belts, the strange and highly inclined orbits of the small, icy bodies in the outer solar system. All of these are clues, are fossils, that point to a history that is far more violent and far more complex than the serene and seemingly peaceful solar system we see today. If we ever develop the technology to send spacecraft on long, multi-generational journeys to explore the vast and largely unknown reaches of the Oort cloud, we may one day find direct and stunning evidence of these lost ancient moons. Perhaps we will even find the frozen and perfectly preserved remnants of worlds that were once a part of our own familiar cosmic neighborhood. But for now, these lost moons remain a deep and beautiful mystery, hidden forever beyond our reach. Some may still be orbiting, dark and unnoticed, in the vast, cold expanse of the outer solar system. Some may be buried, deep and forever, in the distant, icy graveyard of the Oort cloud. And many, many others have likely left us forever, drifting, dark and alone, In the endless, silent emptiness between the stars, we may never know their names, we may never see their shapes, we may never learn their stories, but they're silent and ghostly. Absence is a powerful and deeply poignant reminder of the profound and often tragic impermanence of celestial bodies, a reminder of the way that the cosmos is constantly shifting, constantly changing, and constantly reshaping itself in a beautiful and often violent and eternal cosmic dance. The universe is full of forgotten worlds, and among them, silent and unseen, are the lost, lonely moons of our own, ancient past, silent travelers, forever unremembered, but forever a part of the grand and ongoing story of our solar system. The universe is in constant and often dramatic motion. It is a vast and dynamic expanse, a place where entire galaxies, each containing hundreds of billions of stars, are not just floating aimlessly in the void, but are drifting and often racing through space, bound together by the invisible and powerful threads of gravity. Our own Milky Way galaxy, along with its retinue of smaller satellite galaxies, is not a static island universe. It is part of a much larger cosmic flow, a grand celestial river of galaxies that is being pulled with immense and inexorable force towards something massive, something mysterious, something that we cannot even directly see. This unseen and incredibly powerful gravitational force is known as the Great Attractor, a vast and diffused gravitational anomaly that is so powerful, so massive, that it is drawing entire clusters of galaxies, including our own, towards it at almost unimaginable speeds. And yet, for all of its profound and universe-shaping influence, we cannot see it. The Great Attractor lies hidden, shrouded, and tantalizingly behind the thick and obscuring veil of our own galaxy's dusty, star-filled plain, a region of the sky known as the zone of avoidance, making it one of the greatest and most frustrating mysteries in all of modern cosmology. To understand the true significance and the deep mystery of the Great Attractor, we must first zoom out and look at the large-scale structure of the universe itself. Galaxies are not scattered randomly and uniformly throughout space. Instead, they are arranged in a vast and beautiful cosmic web, a network of immense, interconnected filaments of galaxies, surrounding vast and largely empty cosmic voids. Our own Milky Way is a member of a small and relatively modest collection of about 50 galaxies known as the Local Group. And this local group is itself just a small suburban outpost on the edge of a much, much larger structure, a massive supercluster of galaxies known as the Laniakea supercluster. This cosmic behemoth, whose name means immeasurable heaven in Hawaiian, contains over 100,000 galaxies, all gravitationally bound and all moving, more or less, in the same general direction through space. And that direction, as astronomers have painstakingly discovered by measuring the subtle motions of thousands of galaxies, is directly towards the mysterious and unseen Great Attractor. The gravitational pull of the Great Attractor is enormous. Our own galaxy, the Milky Way, is being pulled towards it at a staggering speed of about 600 kilometers per second, which is over 1.3 million miles per hour. And everything else in our cosmic neighborhood, including the entire massive Virgo cluster of galaxies and all the other nearby galaxy groups, is also moving in the same general direction, all caught in the same powerful gravitational current. This coherent, large-scale flow of galaxies strongly suggests the presence of an immense and previously unknown concentration of mass, a mass that is far, far larger than anything in our immediate cosmic vicinity. And yet, when astronomers have tried to pinpoint the source of this immense gravitational pull, they have run into a formidable and deeply frustrating problem. The center of this gravitational anomaly is located in a part of the sky that is almost completely obscured by the dense and intervening clouds of gas, dust, and stars of our own Milky Way's galactic plane. This region, the zone of avoidance, acts like a thick cosmic fog, blocking our view and making direct optical observations of what lies beyond it almost completely impossible. For decades, scientists have struggled to understand what lies behind this cosmic barrier. If the Great Attractor is so incredibly massive that it can influence the motion of entire superclusters of galaxies, then why can we not see it? The answer, it seems, lies in the way that mass is distributed in the universe, unlike a single, compact object, like a supermassive black hole or a dense, collapsed star. The Great Attractor is not a single, well-defined body. It is, instead, a vast and highly diffuse region of space, a place where the density of galaxies and of the invisible dark matter that surrounds them is particularly high. It is the combined and immense gravitational pull of all these individual and often faint structures that creates the powerful and large-scale gravitational attraction that we observe. But because this mass is spread out over such a vast and distant region of space, it does not emit a single concentrated point of light, like a bright star or a quasar would, making it even more difficult to detect and to study. Despite these immense challenges, astronomers, with their characteristic ingenuity and perseverance, have found clever and indirect ways to study the Great Attractor. By using radio waves and X-ray telescopes, which can penetrate through the obscuring dust and gas of the Milky Way's plane far more effectively than visible light, scientists have been able to detect some of the galaxies and galaxy clusters that reside within this hidden cosmic region. And these observations have revealed a tantalizing and even more complex picture. They suggest that the Great Attractor itself is not the final, ultimate source of the gravitational pull, but is, in fact, just one part of an even larger and even more massive structure, a colossal supercluster of galaxies known as the Shapley supercluster. The Shapley supercluster is one of the most massive and most densely populated concentrations of galaxies in the entire observable universe. It contains thousands of individual galaxies, all packed together in a relatively small volume of space, and it is now thought to be the true primary source of the immense gravitational pull that is affecting our entire local region of the cosmos. But the mystery does not end there. Even beyond the immense gravitational influence of the Shapley supercluster, astronomers have found evidence that our entire local supercluster, Laniakea, is being influenced by another, even more distant and even more powerful cosmic force. This has led to the discovery of what is known as the dipole repeller, a vast and largely empty cosmic void that is, in effect, pushing us away. While the Great Attractor and the Shapley supercluster are pulling us forward, the cosmic motion of our galaxy, it seems, is the result of a complex gravitational tug-of-war, a delicate and beautiful dance between the immense, attractive forces of the great cosmic structures on one side and the subtle, repulsive forces of the great cosmic voids on the other. This suggests that the universe is shaped by even larger and even more complex forces than we had ever imagined, forces that extend far beyond what we can currently, and perhaps ever, directly observe. One of the most intriguing and most important aspects of the mystery of the Great Attractor is the central and largely unknown role of dark matter. The ordinary baryonic matter that makes up the stars, the planets, the gas, and the dust that we can see accounts for only a small and almost insignificant fraction of the universe's total mass. The vast majority of the matter in the cosmos, about 85% of it, is composed of a mysterious and completely invisible substance that we call dark matter. We know it is there because we can see its immense gravitational effects. But we do not know what it is, and it is entirely possible, and even likely, that the immense gravitational pull of the Great Attractor is not just the result of the visible baryonic galaxies that we can, with great difficulty, detect within the zone of avoidance. It is also, and perhaps primarily, the result of a vast and completely unseen concentration of this mysterious dark matter. If this is the case, then our inability to directly and clearly observe the Great Attractor is not just due to the obscuring fog of our own Milky Way, but also, and more fundamentally, because the vast majority of its mass is made up of a strange and invisible substance that we still do not fully understand. As our technology continues to advance, astronomers are developing new and ever more powerful ways to peer into the hidden and forbidden corners of our universe, new and more sensitive. Infrared and radio telescopes are continuing to provide us with clearer and more detailed glimpses of the galaxies that lie within the zone of avoidance and future. Next-generation space missions may offer even deeper and more profound insights. The Vera C. Rubin Observatory, a massive new telescope that is set to begin its survey of the southern sky in the coming years, will provide an unprecedented and wide-field map of the universe, and it may uncover new and crucial clues about the nature of the Great Attractor and its place in the grand cosmic structure. Similarly, the successors to the James Webb Space Telescope could help us to refine our understanding of this profound gravitational enigma. But for now, the Great Attractor remains one of the most intriguing, most elusive, and most beautiful of all cosmic mysteries. We know it is there. We can feel its inexorable gravitational pull, and yet we cannot fully or clearly see it. It is a powerful and deeply humbling reminder that despite all the remarkable and often stunning progress we have made in our quest to understand the universe, there are still vast and powerful forces that are shaping our cosmic destiny, forces that remain, for now, completely hidden from our view. Perhaps one day, with the right new tools and with the right new theoretical insights, we will finally be able to unveil the true and full nature of the Great Attractor and to understand its central and profound place in the grand and beautiful structure of the cosmos. But until then, we continue to race towards it at over 1,000,000 miles per hour, bound by the silent and invisible threads of gravity that so beautifully and so mysteriously weave our entire universe together. In the vast and often bizarre menagerie of the cosmos, among all the strange and wonderful particles that make up our reality, there are some that are so elusive, so ghostly, so profoundly interactive, that they can pass through entire planets, through stars, through galaxies, without ever leaving a single detectable trace. These are the neutrinos, the little neutral ones, the shyest and most mysterious of all the known fundamental particles. But there may be an even stranger and even more elusive version of these particles, a hypothetical entity that is so undetectable, so intangible, so completely and utterly disconnected from our familiar physical world that it could be all around us, passing through us and shaping the very evolution of our universe, without us ever being able to directly know it. These are the sterile neutrinos, the true and ultimate ghost particles of the universe. And if they exist, they may hold the key to some of the deepest and most profound mysteries in all of modern physics. To understand the strange and wonderful nature of sterile neutrinos, we must first look at their more familiar and already quite strange relatives, the three known flavors of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. These neutrinos are produced in incredible abundance throughout the entire universe, emerging from the fiery nuclear reactions in the hearts of stars, from the cataclysmic, explosive deaths of supernovae, and even from the decay of radioactive elements here on Earth. Every single second, trillions upon trillions of neutrinos, mostly from our own sun, are passing through your body without you ever noticing, without them ever leaving a single discernible trace. This is because neutrinos interact with other matter only through the weak nuclear force, one of the four fundamental forces of nature, and this force, as its name suggests, is incredibly weak. A neutrino could travel through a light year of solid lead without ever hitting a single atom. And yet, for all their near invisibility, physicists, with their characteristic ingenuity, have been able to detect and to study these neutrinos. They have built giant and often beautiful underground detectors, massive tanks filled with thousands of tons of ultra-pure water or liquid argon, buried deep beneath mountains to shield them from the confusing noise of other, more interactive, cosmic rays. And in these vast, silent chambers, the rarest of the rare, quantum interactions between a neutrino and an atom can be detected, leaving behind a faint and beautiful trace of its ghostly passage. But sterile neutrinos, if they exist, would be something else entirely. Unlike the three known types of neutrinos, which all participate in the weak nuclear force, sterile neutrinos are theorized to not interact with ordinary matter at all, not even through this incredibly weak force. The only influence they would have on the universe would be through the universal and all-pervasive force of gravity. This means that even our most advanced and most sensitive neutrino detectors would be completely and utterly blind to them. If sterile neutrinos exist, they could be the most elusive and most mysterious form of matter in the entire universe, hidden from us in plain sight. Their presence felt only through the subtle and often ambiguous pull of their collective gravitational weight. The idea of the sterile neutrino, as strange as it may sound, is not just a wild, ad hoc speculation. It arises naturally from several deep and as yet unresolved mysteries in our current understanding of physics. One of the biggest of these puzzles is the very fact that neutrinos have mass at all. In the standard model of particle physics, the incredibly successful theory that describes all the known fundamental particles and their interactions, neutrinos were originally thought to be completely massless, like the photon, but a series of brilliant and Nobel Prize-winning experiments in the late 1990s and early 2000s showed that neutrinos do, in fact, have a tiny, but non-zero, mass. This was a revolutionary discovery, as it was the first direct experimental evidence for physics beyond the standard model. And one of the most elegant and most popular theoretical explanations for the origin of neutrino mass is the seesaw mechanism, a model that requires the existence of a new and much heavier type of neutrino that does not interact through the weak force. This would be the sterile neutrino, another and more direct clue that points to the possible existence of sterile neutrinos comes from a series of strange and still unexplained anomalies in the data from several different neutrino experiments. Experiments like the liquid scintillator neutrino detector at Los Alamos in the 1990s and the more recent Mini-Boone AA experiment at Fermilab have observed in excess of certain types of neutrino oscillations, the process by which neutrinos can change their flavor as they travel through space that cannot be easily explained by the three known types of neutrinos alone. One possible and very exciting explanation for these anomalies is that there is a fourth, and as yet undiscovered, type of neutrino, a sterile neutrino that is mixing with the other three, creating a new and more complex pattern of oscillations. And if sterile neutrinos exist, they could also help to solve one of the greatest and most enduring mysteries in all of cosmology, the nature of dark matter. Dark matter, as we have seen, is the invisible gravitational substance that makes up about 27% of the total mass energy content of the universe. We know it is there, but we do not know what it is. Some theories propose that sterile neutrinos, if they have the right mass, could be a form of warm dark matter, a candidate that could explain some of the subtle discrepancies between the predictions of the standard cold dark matter model and the observed structure of galaxies on small scales. If this is the case, then the universe is filled with a vast and ghostly sea of these sterile neutrinos, their collective gravity shaping the evolution of the cosmos, while they themselves remain almost completely and utterly undetectable. The challenge, of course, the great and deeply frustrating challenge, is to find a way to prove that these ghostly sterile neutrinos actually exist, because they do not participate in the weak nuclear force. Our current direct detection methods are completely useless, so scientists have been forced to get creative, to look for the subtle, indirect signatures of their existence. The search for anomalous neutrino oscillations continues, with new and more powerful experiments, like the Deep Underground Neutrino Experiment, which will send a beam of neutrinos 800 miles through the Earth from Fermilab in Illinois to a massive underground detector in South Dakota, hoping to measure the properties of neutrino oscillations with unprecedented precision. Other experiments are looking for the faint, X-ray signals that could be produced by the very slow decay of sterile neutrinos over cosmological timescales. And some are even looking for the subtle, gravitational effects that a large population of sterile neutrinos could have on the structure of the early universe, as seen in the faint, ancient light of the cosmic microwave background. But so far, no definitive and universally accepted evidence has been found. The implications of discovering a sterile neutrino would be truly enormous. It would not just force us to rewrite the textbooks of particle physics, it could also fundamentally reshape our understanding of the universe's composition, its history, and its evolution. It might even provide a crucial clue to another deep and related mystery, the matter-antimatter asymmetry of the universe. According to our current understanding of physics, the Big Bang should have produced matter and antimatter in almost exactly equal amounts, and when matter and antimatter meet, they annihilate each other in a flash of pure energy. So, the universe should be filled with nothing but a sea of radiation. But it is not. It is filled with matter, with us. Something, in the first, fiery moments of creation, must have tipped the cosmic scales, creating a tiny but crucial excess of matter over antimatter. The leptogenesis scenario, a leading theoretical explanation for this asymmetry, proposes that the decay of heavy, sterile neutrinos in the early universe could have created this imbalance, a process that is intimately linked to the same seesaw mechanism that gives the light neutrinos their mass. But what if sterile neutrinos are never found? What if they exist, but are truly and fundamentally undetectable? They would remain forever beyond our reach, a ghostly and unprovable presence, their influence on the cosmos felt, but never directly seen. This would be one of the most frustrating and most humbling possibilities in all of physics. A fundamental and perhaps even crucial particle that shapes the very nature of our reality. But that can never be conclusively and definitively proven to exist. It would be like knowing that there is a hidden and powerful force that controls the destiny of the universe, but never being able to touch it, to see it, or to measure it in any way. And yet, the history of science has shown us, again and again, that what seems undetectable today may become observable with the new and often unpredictable technologies of the future. When the neutrino itself was first theorized by Wolfgang Pauli in the 1930s, many physicists, including Pauli himself, believed that it would never be detected, as it was thought to interact far too weakly with matter. But decades later, clever and patient, experimentalists built the giant underground detectors that proved that neutrinos were real. Perhaps one day, a new and even more clever breakthrough in physics will allow us to indirectly but unambiguously confirm the existence of sterile neutrinos, unlocking one of the final and most profound secrets of the cosmos. But until then, sterile neutrinos will remain a beautiful and deeply tantalizing possibility, a ghostly whisper in the grand cosmic symphony, a silent and powerful force that may exist forever, just beyond our grasp, whether they are the key to the mystery of dark matter, the answer to the puzzle of cosmic asymmetry, or merely a phantom, a beautiful and ultimately incorrect prediction that will lead us in new and even more interesting directions. They're profound and beautiful. Mystery continues to haunt the very frontiers of modern physics. For as long as humans have gazed up at the night sky, for as long as we have been conscious, questioning beings, we have wondered where everything came from. The prevailing and remarkably successful scientific theory is that our universe began approximately 13.8 billion years ago, in a hot, dense, and incredibly energetic event that we call the Big Bang. Everything we see today, the stars, the galaxies, the planets, and even the very fabric of space and time itself was born from this single, momentous, and transformative moment of creation. But this powerful and well-tested explanation inevitably raises a deeper and perhaps even more profound question: what came before the Big Bang? Was there a time before time? Did our universe simply and miraculously emerge from a state of absolute nothingness? Or has the universe, in some strange and perhaps unrecognizable form, always existed? And if it has, are all the past, and perhaps infinite, versions of our reality lost to us forever? Their histories, their stories, their very existence erased like fleeting, ephemeral footprints on a vast and timeless cosmic shore. One of the most perplexing and most humbling ideas in all of modern physics is that the very concept of time itself may have begun with the Big Bang. According to Einstein's general theory of relativity, space and time are not separate, independent entities. They are two inseparable aspects of a single, unified, four-dimensional fabric that we call space-time. And if the universe, if space, had a beginning, then it seems that time itself must have also had a beginning. This means that asking the question, what came before to the Big Bang, might be like asking the question, what is north of the North Pole? It may be a question that is not just unanswerable, but is, in a fundamental, logical sense, meaningless. However, many physicists and many philosophers are not satisfied with this seemingly simple and somewhat dismissive answer. If the universe and time itself simply sprang into existence from nothing, then what determined the specific laws of physics that govern it? Why does the universe exist at all, with all its beauty and its complexity? instead of simply remaining in a state of eternal, empty, and timeless void. These deep and perhaps unanswerable questions have led scientists to explore other, more exotic and more mind-bending possibilities, including the idea that the universe is, in fact, eternal and has always existed in some strange and cyclical form. One of the most popular and most elegant of these alternative theories is the idea of a cyclic universe. Instead of beginning from a state of absolute and singular nothingness, the universe may go through an endless and perhaps eternal series of expansions and contractions, much like a great cosmic heartbeat. In this model, the Big Bang was not the true, absolute beginning of all things, but was merely the latest rebirth of the universe, before our current expanding universe. There may have been another, and perhaps very different, universe. A universe that expanded, that cooled, that formed its own stars and galaxies, and that then, eventually, collapsed back in on itself in a fiery Big Crunch. A cataclysmic event that then, in turn, gave rise to the Big Bang of our own cosmic eon. And if this process has been happening forever, then the universe has no true, single starting point. It has only an endless and beautiful cycle of creation and destruction, of death and rebirth. But if the universe is truly cyclical, if it has gone through a potentially infinite number of past iterations, then what happened to all of those previous universes? Why do we have no memory, no record, no physical evidence of their existence? The answer, it seems, may lie in the relentless and unforgiving arrow of time, the second law of thermodynamics. With each new cycle of the universe, the total entropy, the total amount of disorder, should increase. This means that even if a new universe is born from the ashes of the old, it will not be an exact copy. The information from the previous cycle, the detailed record of its history, its structure, its life, is effectively lost, scrambled, and erased in the fiery and high entropy crucible of the bounce from a Big Crunch to a Big Bang. This means that even if there have been an infinite number of past universes, they have each, in their own turn, left no discernible and recoverable trace behind. Everything that came before us in this cyclic picture has been effectively and completely erased, making it impossible for us to ever recover any direct and detailed knowledge of what happened before our own local Big Bang. Another, and equally profound, possibility is the idea of the multiverse. Instead of a single universe that cycles through different sequential stages, there may be an infinite and coexisting number of other parallel universes, each with its own unique beginning, its own unique history, and its own unique set of physical laws. In some versions of this theory, like the eternal inflation model, new bubble universes are constantly being born in a vast and ever-expanding cosmic landscape, each one emerging from a random quantum fluctuation or from a localized, phase transition-like expansion of space-time. If this is true, then what came before our own Big Bang was not a single previous universe, but a vast and complex multiversal reality, a cosmic foam where every possible and conceivable reality exists somewhere in its own self-contained bubble. But even the multiverse does not fully or satisfyingly answer the question of an infinite past. If there are many and perhaps an infinite number of other universes, then where did they come from? Has the multiverse itself always existed, or did it, too, have a beginning? Some scientists and philosophers have proposed that the very concept of time itself may not be a fundamental aspect of reality, that what we experience as the linear to forward flow of time is just a human, and ultimately illusory, perception of a much deeper and perhaps timeless reality. If time is an emergent property rather than a fundamental feature of the universe, then the very question of what came before the Big Bang may not have a meaningful or even a sensible answer at all. The universe, in this sense, may simply be a timeless and eternal mathematical structure without a beginning or an end. However, there is one formidable and perhaps insurmountable problem that remains, regardless of which of these grand cosmological stories we choose to believe, and that is the nature of the Big Bang itself. If we could somehow, with our theories and our instruments, peer back far enough into the past, beyond even the first fleeting moments of our universe's existence, we might be able to find some direct and unambiguous clues about what came before. But the problem is that our current and remarkably successful physical theories, the theories of general relativity and quantum mechanics, break down at the very moment of the Big Bang. The extreme and infinite density and energy of the early universe create a singularity, a point in space-time where our laws of physics cease to have any meaning, where our equations give nonsensical, infinite answers. This singularity acts like a great and impenetrable cosmic curtain, blocking us from ever being able to see or to know anything that lies beyond it, unless we can somehow develop a new and more complete theory of physics, a theory of quantum gravity that can describe what happens at and beyond the singularity. The ultimate past, the time before the Big Bang, may forever remain a deep and beautiful mystery, despite these immense and perhaps even fundamental challenges. Some scientists believe that we may still be able to find some indirect and circumstantial evidence of a time before the Big Bang. If the universe is truly cyclical, there might be subtle and almost imperceptible imprints of the previous universes left behind in the faint, ancient glow of the cosmic microwave background. Some researchers have suggested that certain large-scale circular patterns in the temperature of this radiation could be the ghostly and beautiful remnants of the black hole collisions that occurred in the previous cosmic eon. So far, no such conclusive evidence has been found. Similarly, if the multiverse is real, then the collision of our own bubble universe with another could have left a cosmic bruise, a subtle and detectable distortion in the distribution of galaxies on the largest scales. But what if we will never, ever truly know the answer? What if the past is, in fact, lost to us forever, hidden behind an impenetrable and eternal wall of cosmic history? If that is the case, then the true nature of the infinite past may remain one of the greatest and most beautiful of all unanswered questions in science. We may live in a universe that, by its very nature, erases its own history, a universe that is constantly being reborn, a universe that leaves us with only the fleeting and beautiful present moment, and a deep and enduring mystery that stretches forever and silently into the endless and unknowable past. And still, the search for answers continues. Every new discovery, every new theory, brings us just a little bit closer to understanding the true and ultimate origins of our own cosmic reality. And perhaps one day, a new and brilliant breakthrough in physics will reveal a deeper and more profound truth about the nature of space, of time, and of existence itself. But until then, we are left to wonder, was there something before the Big Bang? Or has the universe, in some strange and beautiful and perhaps cyclical. Form, always been, stretching back, forever, into an infinite and timeless past that we can never, ever truly grasp. The search for intelligent life beyond our own small and fragile planet is a question that has haunted the human imagination for centuries. With an estimated 2 trillion galaxies in our observable universe, each filled with hundreds of billions of stars, and with the recent discovery of countless and often Earth-like planets orbiting those stars, it seems almost a statistical impossibility that we are alone. The sheer, overwhelming numbers suggest that life, and perhaps even intelligent and technological life, should have arisen many, many times throughout the long and often violent history of the cosmos. And yet, when we turn our radio telescopes to the heavens, when we listen for the faint and telltale whispers of a distant alien civilization, the universe is eerily and profoundly silent. We have been listening with ever-increasing sensitivity for decades now, scanning the vast and seemingly empty expanse of the sky for any sign, for any signal, for any single anomalous blip that would tell us that we are not alone. But we hear nothing. If intelligent life is truly a common and perhaps even an inevitable outcome of the laws of physics and biology, then where is everyone? This is the simple and deeply unsettling question at the heart of the Fermi paradox, a paradox that pits the high statistical probability of extraterrestrial intelligence against the complete and deafening lack of any evidence for it. One of the most sober and most plausible possibilities is that other intelligent civilizations once existed, but are now long and tragically gone. The universe is ancient, more than 13.8 billion years old. This is an almost unimaginable expanse of time, a time scale upon which entire species, entire civilizations, entire biospheres could have evolved, could have flourished, and could have vanished. Millions or even billions of years before human beings ever walked the earth. If alien civilizations rose and fell long before we ever developed the technology to detect them, then we have, in a cosmic sense, simply missed them, their messages, their probes, their great interstellar broadcasts, if they ever sent any, may have passed through our small corner of the galaxy thousands or even millions of years ago, long before we had the means or the inclination to listen. Or worse, their signals might still be on their way, a faint and lonely whisper from a long-dead civilization. A message in a bottle that will only arrive at our shores long after our own. Human civilization has itself ceased to exist. This idea that civilizations do not last is a troubling but powerful answer to the Fermi paradox. It suggests that the cosmos may be filled not with thriving interstellar empires, but with the silent and ghostly remnants of once great civilizations, with dead and barren worlds where advanced and perhaps even beautiful beings once lived but are now reduced to a final and eternal silence. There are many, and often terrifying, possible reasons why intelligent and technological civilizations might not endure for very long on a cosmic time scale. One of the most widely and most anxiously discussed of these ideas is the concept of the Great Filter, a hypothetical and seemingly insurmountable barrier that prevents most, if not all, civilizations from ever advancing beyond a certain critical stage. If this filter lies in our past, then it would mean that the emergence of life, or of intelligence, or of technology, is an incredibly and almost miraculously rare event, and that we, as a species, are one of the first and perhaps the only intelligent beings to have ever reached this point in our galaxy. But if the filter lies in our future, then it suggests a far more ominous and far more chilling possibility that all, or nearly all, advanced civilizations, like our own, inevitably, and perhaps even predictably, destroy themselves before they ever reach the level of stable, long-term, interstellar expansion. The ways in which a civilization might self-destruct are numerous, and all too familiar to us. Nuclear war is an obvious and terrifying possibility. A species that develops the incredible and almost godlike power to split the atom gains access to a source of almost limitless energy. But it also, and at the very same time, gains the ability to wipe itself out in a final and fiery instant. If alien civilizations had the same, and often self-destructive, political and social structures as our own, then they may have been just as prone to conflict, to tribalism, to war, and a war fought with weapons far beyond our current, and already terrifying. Technology could have left their entire home planets uninhabitable, extinguishing the bright and precious flame of intelligent life before it ever had the chance to spread beyond its own fragile and war-torn world, another and perhaps even more insidious possibility is environmental collapse, a highly advanced and highly successful technological civilization may, like our own, become deeply and perhaps fatally dependent on the finite resources of its home planet, consuming them at an ever-increasing and ultimately unsustainable rate. If they fail to manage their own technological success, if they fail to transition to a more sustainable and more harmonious way of life, they may have depleted their own ecosystems, they may have poisoned their own atmospheres, they may have altered their own climates beyond the point of recovery. Rising temperatures, failing crops, collapsing biospheres, these could have doomed them, leaving their once thriving and once beautiful worlds barren, silent, and dead. If civilizations repeatedly and predictably destroy their own planetary homes before they ever develop the means to leave them, then the galaxy could be filled with a vast and tragic graveyard of dead worlds. Worlds that once hosted the bright and fleeting promise of intelligent life. And then there are the biological threats. A civilization that advances to the point of being able to manipulate its own genetic code to master the arts of genetic engineering and synthetic biology might also, and perhaps inevitably, create diseases that it cannot control. Pandemics, whether natural or artificial, could have swept through their populations, wiping them out in a matter of years. And if intelligent beings experimented with altering their own biological nature, perhaps in the noble pursuit of immortality, or of enhanced intelligence, or of a new and more perfect form of artificial evolution, they may have, with the best of intentions, unintentionally engineered their own and final downfalls. But what if civilizations do not destroy themselves intentionally? Some may have simply been the victims of a cruel and indifferent cosmic chance. They may have fallen victim to the many, and often unpredictable, external threats that the universe can throw at a fragile and planetary biosphere. A massive and civilization-ending asteroid impact, a supervolcanic eruption that plunges their world into a long and deadly volcanic winter, a nearby and powerful gamma-ray burst, the focused and incredibly energetic beam of radiation from a collapsing, massive star that could have sterilized their entire planet in a single, silent flash. Even if a civilization became a spacefaring one, Even if they had managed to establish outposts on other planets or moons in their own solar system, they may still have been caught in the path of a truly and unimaginably catastrophic cosmic event. A rogue and wandering black hole, a close and violent collision between two stars, a nearby and powerful supernova explosion if their entire long-term survival depended on the stability of a single and ultimately fragile planetary or even a single star system. Then the destruction of their home could have meant the final and absolute end of their entire and perhaps billion-year-long species. There is also the even more unsettling and more paranoid possibility that some civilizations were not alone, but that they encountered others who did not have peaceful or even collaborative intentions. If intelligent and technological, species are, by their very nature, competitive and expansionist, then the first civilization to develop the means of interstellar travel might have, as a matter of cold and ruthless logic, viewed any other emerging civilizations as a potential future threat, a threat to be monitored and perhaps to be eliminated. This is the dark and chilling logic of the dark forest hypothesis, a possible solution to the Fermi paradox that suggests that advanced civilizations remain silent, not because they do not exist, but because they are terrified of attracting the attention of others. If every advanced species assumes that any other species might be hostile, then the safest and most logical course of action is to remain completely and utterly hidden. Those that have, in their naivety, revealed their presence, those that have broadcast their existence to the stars, may have been quickly and silently destroyed. Their bright and hopeful signals a final and tragic beacon that led to their own swift and merciless extinction. If this is true, then the universe might not be empty at all. It might simply be full of a vast and silent population of terrified and hiding civilizations, each one listening and waiting in the dark. And even if some rare and perhaps very lucky civilizations manage to survive all of these immense and often self-inflicted threats, there is still the final and perhaps most profound issue of all, the issue of time itself. The universe operates on a timescale that is so vast, so deep, so almost unimaginably long, that it dwarfs the lifespan of even the most ancient and most stable of civilizations. If an alien civilization flourished 1 billion years ago, and if it lasted for 1 million or even 10 million years before it finally collapsed or disappeared, that would still be an unimaginably long and successful lifespan for a civilization. But in the grand 14 billion year long timeline of the cosmos, it would be nothing more than a fleeting and almost imperceptible moment. If civilizations emerge and then disappear on timescales that are separated by millions or even billions of years, then the likelihood of two independent, intelligent species existing at the same time and also being close enough in space to detect each other is incredibly, vanishingly low. We may have simply arrived too late to the cosmic party, or too early, but perhaps civilizations do not vanish in a final, fiery destruction. Perhaps, instead, they simply retreat. They retreat inward, asufficiently, and perhaps unimaginably. Advanced species may, at some point, simply abandon the messy, difficult, and often dangerous project of physical and interstellar exploration altogether. If their technology reaches the point where they can create perfect and completely immersive virtual worlds, if they can upload their consciousnesses into vast and powerful computational machines, they may have no need and no desire to continue to explore the physical and often disappointing universe. They could have transferred their entire collective existence into a new and more perfect digital space, leaving behind only the silent and empty, planets and the dark and rusting, cities of their physical and now abandoned past. If this is the case, then the answer to the Fermi paradox is not that civilizations do not last, but that they evolve beyond what we can recognize, beyond what we can detect, beyond what we can even comprehend, the most haunting and most lonely possibility of all, however, is that we are, in fact, the first. That intelligent and technological, life is so incredibly and so miraculously rare that we are at this moment the only and the first conscious beings in our entire galaxy, and perhaps even in our entire observable universe, to have reached this particular and perhaps very dangerous stage of development. If this is true, then we are standing at a profound and deeply significant cosmic precipice, facing a choice that may have determined the fate of all those who came before us, if they ever existed at all. We have the potential, the incredible and beautiful potential, to become the first civilization to break free from the Great Filter, to survive our own technological adolescence, to expand beyond our own fragile planet, and to spread the light of life and of consciousness out into the vast and silent stars. But we also face the very same and very real dangers that may have doomed countless and now forgotten others. The silence of the cosmos in this light is not just a scientific mystery. It is a profound and deeply moving warning. If civilizations before us have, in their pride and their folly, destroyed themselves, then we must, with all our collective wisdom and our deepest humility, learn from their silent and tragic mistakes. And if the universe is truly and completely empty, then the great and sacred responsibility falls on us, and on us alone, to ensure that the beautiful and precious experiment of intelligent life does not end here, with humanity. We have the ability, the technology, the knowledge to shape our own future, to decide whether we will be just another lost and forgotten civilization, or the first, and perhaps the only, to endure. For now, we continue to search, we continue to listen for the faint and hopeful signals from a distant star. We continue to send our own small and fragile messages out into the vast and silent void. And we continue to hope that we are not too late or too early. Perhaps one day we will hear something, a whisper from a distant star, a faint and beautiful trace of a civilization that survived where others, perhaps, have failed. But until then, we are left with the great and profound silence. And we are left to wonder whether it is the silent and tragic echo of all those who came before us, or the deep and lonely absence of anyone at all. The ultimate fate of our universe is one of the most profound, most beautiful, and most unsettling mysteries in all of cosmology. We exist in a universe that we know had a definite and fiery beginning in the Big Bang. But what happens at the end? Will everything collapse back in on itself in a final cosmic inferno? Will it tear itself apart into a state of absolute and chaotic oblivion? Or will it simply and silently fade away into a cold, dark, and eternal nothingness? No matter which of these grand and often terrifying scenarios plays out, there will be a final and absolute horizon, a point in the far to distant future where no observer, no matter how advanced, no matter how patient, will ever be able to witness what comes next. The very end of the universe will not just be lost to us, it will be lost to all of existence itself. To understand the future, we must first look to the past and to the present. The universe, as we have seen, began with the Big Bang, a moment of almost unimaginable energy and expansion that marked the creation of space and time itself. And from that initial, singular moment, everything has been expanding outwards, forming the vast and beautiful tapestry of galaxies, of stars, of planets that we see today. But the force that first set the universe in motion, the force of expansion, has never stopped. For the first few billion years of cosmic history, the force of gravity, the mutual attractive pull of all the matter in the universe, acted as a powerful cosmic brake, slowing down the rate of this expansion. But then, about 5 billion years ago, something changed. A new and mysterious force, an invisible and repulsive energy that we call dark energy, began to win the cosmic tug of war. And today, we know that dark energy is not just winning, it is dominant. The universe is not just expanding, its expansion is accelerating, growing faster and faster with each passing moment. And as time goes on, the distant galaxies will continue to drift farther and farther apart. What we see in our night sky today, the beautiful and seemingly eternal spiral and elliptical galaxies, will look drastically different in the far distant future. Eventually, one by one, these entire and magnificent island universes will disappear from our view, slipping silently and irrevocably beyond our cosmic event horizon, their light forever unable to reach us again. This alone is a strange and deeply terrifying thought. One by one, the universe is erasing itself from our own local perspective. But the true and ultimate fate of our universe depends entirely on the nature and the future behavior of this strange and mysterious dark energy. And scientists have theorized several possible and often haunting endings to our cosmic story. One of the most dramatic and most violent of these possible endings is the Big Rip. If dark energy is not a constant, but is a form of phantom energy that grows stronger and more repulsive over time, then it will not just continue to push the distant galaxies apart, it will eventually begin to tear apart the very fabric of reality itself. First, the great clusters of galaxies, the largest gravitationally bound structures in the universe, will be dissolved, their constituent galaxies flung out into the expanding void. Then, as the repulsive force of the phantom energy continues to grow, it will overcome the gravity of the individual galaxies themselves, breaking them apart, and leaving their billions of stars stranded and alone in the darkness. As the end approaches, the force will become so strong that it will overcome the gravity that holds our own solar system together, tearing the planets from their orbits and leaving them to wander, dark and cold, through an increasingly and violently unstable reality. Eventually, in the final, fleeting moments of the cosmos, the force of the Big Rip will overcome the electromagnetic forces that hold the atoms themselves together. And then, finally, the strong nuclear force that binds the protons and the neutrons in the atomic nucleus. Everything, matter, space, and perhaps even time itself will be ripped apart at the most fundamental subatomic level. The universe will not just end, it will be violently and completely destroyed, its every structure, at every scale, reduced to a shower of free and causally disconnected fundamental particles. But there is another, and perhaps even quieter and more haunting fate that may await us, the heat death, also known as the Big Freeze. In this scenario, the cosmic expansion, driven by a constant dark energy, continues, but at a steady and ever accelerating rate. The universe will continue to spread all of its matter and energy out over an ever larger volume of space until nothing can ever interact with anything else again. The stars will slowly and one by one exhaust their nuclear fuel. They're bright and beautiful, flames flickering and dying out, leaving behind only the cold, dark, and silent remnants of white dwarfs, neutron stars, and black holes. The galaxies themselves will fade into an eternal darkness, and then, over immense and almost unimaginable timescales, even these last remaining structures will begin to decay. The protons themselves may, according to some theories, be unstable and will, over trillions upon trillions of years, slowly decay into a sea of lighter particles and radiation. And the black holes, the last and most massive structures in the universe, will slowly and silently evaporate, radiating away their mass energy through the subtle quantum process of Hawking radiation. In the end, after an almost infinite amount of time has passed, the universe will be a cold, dark, empty, and lifeless place. There will be no new stars being born. There will be no galaxies colliding. There will be no motion, no warmth, no change. The universe will not have exploded. It will not have collapsed. It will have simply and quietly stopped doing anything at all. This is, for many, the most haunting and most existentially terrifying of all possible endings. Not a fiery and dramatic cataclysm, but a slow, cold, and inevitable fading into an absolute and eternal nothingness. And the worst and most poignant part of this story is that no one will be left to witness it. If any far future civilizations manage to survive for these billions or even trillions of years, they will slowly and inexorably fade with the dying stars. The last conscious being in the entire universe will have no one to tell their story to, no one to hear their final and lonely words. When the very last usable source of energy in the cosmos is finally used up, existence itself, in all its beauty and its complexity, will go silent. But there is still one more possibility, one that offers the tiniest and perhaps most beautiful glimmer of hope. Some theories, as we have seen, suggest that the universe may be cyclical, that after it fades or after it rips apart, a new universe could be born from its ashes. If this is true, then the end is not truly the end, but is just the beginning of something new, a new chapter in an eternal cosmic story. However, even in this hopeful and beautiful picture, our own universe, our own story, would still be lost. If a new universe is born, it will be completely and utterly disconnected from our own. There will be no way to remember what came before, no trace of the past that can be left behind. Our universe, with all its beauty, all its complexity, all its life, everything that we know, everything that we have ever been, will still be lost forever to the sands of an eternal and unforgiving time. No matter what happens, no matter which of these grand cosmic scenarios plays out, the final and ultimate horizon of our universe is a line that no one and no thing will ever be able to cross. The end will come, and there will be nothing left to see it. It is a thought that is both profoundly humbling and deeply and beautifully sad. The universe is a grand and glorious and ultimately tragic story, and we are living in its middle, and perhaps its most beautiful and most interesting chapter. And the very fact that we are here now to witness it, to understand it, to appreciate its fleeting and beautiful and often terrifying glory, is a miracle that is almost too profound for words. The universe, in all its vast and often mysterious splendor, is an endless expanse of wonder, a cosmic ocean filled with secrets that stretch far beyond the limits of our current, and perhaps even our future, understanding. It is a reality that calls to us, that ignites our curiosity, that fuels our ambition, and that urges us to explore the great, and often terrifying, unknown. And yet, for all our dreams of reaching the stars, for all our technological ingenuity, for all our boundless human perseverance, there are places in this vast and beautiful cosmos that we will never be able to set foot in, realms that are so distant, so hidden, or so fundamentally and physically unreachable that they will remain forever beyond our grasp. These are the forbidden zones of the universe, and no amount of technology, no future, scientific breakthrough, no amount of pure human will ever allow us to breach their silent and eternal boundaries. Some of these forbidden, and often tragic, places are being actively and constantly created right now as we speak, torn from our view by the relentless and ever-accelerating expansion of space itself, with each passing moment entire and magnificent galaxies, each containing billions of stars and perhaps billions of planets, are racing away from us at speeds that are faster than the speed of light, carried along on the ever-growing and ever-stretching fabric of the cosmos. The deeper we look into space, the more we realize just how much of the universe is already, and forever, gone. Regions of the cosmos that were once in the distant and ancient past, within our causal reach, now exist beyond a point, beyond a horizon, that we can never, ever cross. Even if we could somehow, one day, develop the technology for engines that could propel us at the very speed of light itself, it would not be enough. The very space between us and these distant, and now forbidden, realms is expanding too fast for us to ever be able to catch up. And even much closer to home, in our own local cosmic neighborhood, the ultimate barriers of the universe are just as real and just as insurmountable. Black holes, the most enigmatic and most powerful objects in all of existence, hold deep and perhaps eternal secrets that we may never be able to uncover. Their event horizons are not just a physical boundary, they are a one-way and absolute door to oblivion. Anything that crosses this point of no return, no matter how advanced, no matter how powerful, no matter how resilient, will never be able to come back. Not even light, the fastest thing in the universe, can escape their immense and unforgiving gravitational pull. And whatever information, whatever story, whatever reality falls inside is, for all practical purposes, effectively and completely erased from the universe as we know it. The very nature of space and of time within a black hole is a deep and profound mystery to us, and it is a mystery that may be, in its very essence, forever unknowable. If we could somehow send a probe, a robotic emissary, into one of these dark and silent abysses, its signals, its data, its final desperate messages would never be able to reach us. And if an astronaut, a brave and perhaps foolish explorer, were to venture too close, they would be stretched and crushed and torn apart into a stream of fundamental particles, their body, their mind, their story, all reduced to a final and silent nothingness, long before they could ever hope to tell us what they had found. The heart of a black hole is not just a forbidden zone, it is the ultimate and most absolute point of no return. And what about the true and ultimate beginning of everything? The very first fleeting moments after the Big Bang hold the answers to some of the deepest and most profound questions that humanity has ever asked. Questions that could explain our entire and often mysterious existence. And yet, they are locked away from us forever, behind a thick and impenetrable veil of physics that we cannot and may never be able to penetrate. The universe, in its extreme and fiery infancy, was so incredibly hot and so unimaginably dense that light itself, the very photons that carry information across the cosmos, was unable to travel freely. The early universe was an opaque and chaotic fog, and this means that no telescope, no matter how powerful, no matter how sophisticated, will ever be able to directly see what truly happened at the very start. The first and most crucial moments of time itself exist behind an eternal and insurmountable wall, a forbidden zone that is not in space, but in time. But perhaps the most unsettling and most humbling reality of all is not just that there are places and times that we can never reach, but that the number of these forbidden zones is constantly and inexorably growing every single second. New and previously accessible regions of space are drifting silently and forever, beyond our ability to ever explore. The universe is expanding, and with it, the possibilities for our own, human and cosmic, exploration are, in a very real and very tragic sense, shrinking. 1 trillion years from now, there will come a time when our own familiar Milky Way galaxy is the only thing that is visible in the vast and dark night sky. Every other galaxy, every other island universe will have vanished forever, beyond our cosmic horizon, never to be seen again. Future civilizations, no matter how advanced, no matter how curious, will never even know of the vast and beautiful cosmos that we, in our own brief and precious moment of cosmic history, are still able to glimpse. To them, the universe will appear as a lonely and isolated island, a single, solitary galaxy in an infinite and seemingly empty void. And yet, despite knowing all of this, despite knowing that there are limits, that there are boundaries, that there are places we can never go, we continue to reach, we continue to wonder, we continue to dream, even if we can never set foot in these lost and forbidden places. Even if the universe has set certain and absolute limits that we can never, ever cross, our desire, our insatiable and beautiful human desire to understand is limitless. And perhaps, in the end, that is what truly and most profoundly defines us. Not where we can go, but what we seek to know. The forbidden zones of the universe, the lost galaxies, the dark hearts of black holes, the silent and ancient beginning of time, may never be explored in person, but they will always and forever be explored in our minds, in our theories, in our stories, in our dreams, and in that sense, in the beautiful and often tragic and endlessly creative journey of the human imagination. The quest, the exploration, the adventure never, ever truly ends.